can come and occupy. Good morning, esteemed delegates, distinguished guests, and fellow participants. It's my pleasure to welcome you to the second day of our international conference on nanoscience and computational modeling. I hope you had a productive and enriching first day filled with insightful presentation, stimulating discussions, and meaningful computational modeling. Let us now begin the second day of our conference with a small AV.
Throughout its history, since the inception, Sri Manakula Engineering College has been one of the nation's great institutions for the study of the undergraduate and postgraduate programs in various engineering disciplines. The School of Arts and Science is inaugurated during the academic year 2020-2021. Sri Manakula School of Arts and Science has distinctive academic excellence rooted in tradition and culture-based standard curriculum.
Program offered: Department of Professional Studies, Department of Commerce, Department of Corporate Secretaryship, Department of Management, Department of Computer Science, Department of Computer Applications, Department of Basic Sciences, Department of Humanities, Department of Biosciences, Department of Food Science, Department of Media Studies.
Concepts in organic chemistry, exploring scientific research knowledge through spectroscopy research. Career guidance. Industrial visit. Students events. NSS activities. World Ozone Day. National Science Day. Extension activities. Placement. IG, Kalampakam. Department of Physics. On account of Abdul Kalam birthday, planting tree sampling in college. Science Day. National Science Day 2024. Industrial visit to Apasami ocular devices. Webinar on opportunities in physics. Seminar, recent concepts and mysteries in physics. Students participate early in drone technology workshop.
I request our esteemed guests to join us on the dais. We now invite Dr. T. Jayavardhanan, Head of Physics, to deliver the welcome address.
Good morning to one and all, respected dignitaries, esteemed guests, distinguished speakers, and dear participants. It is my pleasure to welcome you all to the second day of the International Conference, Nanoscience and Computational Methods, ICNCM 2025, a platform where knowledge, innovation, and collaboration converge to shape the future. After an insightful and engaging first day, we are excited to continue our journey today with more thought-provoking discussions. This moment is made even more special as we extend a warm and distinguished welcome to our chief guest, Dr. Ramesh L. Gadas, Professor, Department of Chemistry from IIT. I welcome you, sir. A special welcome to our resource person, Dr. S. Santosh Kumar, postdoctoral researcher, Department of Chemistry, National Science University, Taiwan, who is delivering his lecture through online mode. As we embark on the second day, let us continue to engage in meaningful discussions, challenge conventional ideas, and explore innovative solutions to the presenting challenges and our times. Once again, a heartfelt welcome to all present here for the journey as today, wishing you a productive and enriching day ahead. Thank you all.
Thank you, sir. It's the time to honor our chief guest. Now I request Dr. T. Jayavardhanan to honor our chief guest. Thank you, sir. Now I invite Dr. Karthikeyan, Department of Chemistry, Professor, to read the guest profile.
Very good morning to everyone. Myself Dr. Karthikeyan, and I am happy to read the great speaker of the first session of today, Dr. Ramesh L. Goddess. Sir is a professor in the Department of Chemistry at the Indian Institute of Technology, Madras, Chennai. He holds a PhD in chemistry from Veer Narmad South Gujarat University, where his research focused on thermodynamic studies of non-electrolyte liquid mixtures. Dr. Goddess has over 20 years of experience in both academic and research field, with his postdoctoral research conducted in Portugal at the University of Columbia and the University of Aveiro, followed by research position at the Queen University, Belfast, UK. Dr. Goddess has made substantial contribution to the development of non-conventional environmentally vegan solvent systems such as ionic liquids and deep eidetic systems. His work has generated extensively thermodynamic data and structure property correlation that are used in industries such as refrigeration and crude oil processing. A notable achievement is the inclusion of over 18,000 thermodynamic data points generated in his lab in the NIST Standard Reference Database, a key resource for researchers globally. One of his most significant scientific contribution is the development of the Goddess and Computational model, a widely cited method for the predicting the density of ionic liquid across different pressures and temperatures. In his academic career, Dr. Goddess has guided 16 PhD students to the completion, with 8 more currently under his supervision. He has also mentored several postdoctoral researchers and MSc students, has managed numerous research projects, securing funding worth over ₹750 lakhs, that means 7.5 crores, and completing 12 projects as a principal investigator and a co-principal investigator. His research has been published extensively with 236 documents, contributing to a citation count over 9,000 on Google Research Scholar, achieving an I index of 49. His expertise in chemical thermodynamics and solvent systems is recognized internationally. Dr. Goddess has been honored with various prestigious awards, including Indian Research and Development Award, mid-career level, from IIT Chennai, Madras in 2020, and the Professor S.P. Harmath Memorial Award in 2023 from the Indian Council of Chemists. Has been featured in the world ranking of top 2% scientists for several consecutive years. He also served as an associative editor for the Journal of Chemical and Engineering Data and has held editorial position in several other high-impact journals. In addition to his research achievements, Dr. Goddess has delivered more than 320 invited talks worldwide and participated in over 150 conferences. His professional affiliation include fellowship with the Royal Society of Chemistry and Indian Chemical Society, the Academic Sciences Chennai, and the Telangana Academy of Sciences. He is also involved in numerous scientific societies and has contributed to the academic community as a member of Board of Studies multiple universities. Dr. Goddess extensively experience and contribution to the field of chemistry, particularly in the area of thermodynamics and environmentally friendly solvent systems, continue to impact both academic and industrial application globally. With this introduction, I requested Dr. Ramesh sir to take over the session. Welcome, sir. Thank you.
Thank you very much, sir, for extensive reading of my entire CV. So let me start meanwhile when they put it. Good morning. I'll say again whose voice will be louder. Good morning. Maybe one more time. Good morning. Thank you. So, let me start thanking the organizers of this conference for inviting me and excellent opportunity. I see so many people are there, and I was told here largely the students are UG, PG and few research scholars from physics, chemistry, biology. Any other department? No. Yeah. Okay. You see my first slide now, and if collar mic is there, it would be nice. If you check if it is there, it will be great. Collar mic. So let me start telling that if entire world's research, experimental research, both industrial research and academic research, if we can divide into three categories: solid state, solution phase and gas phase research, I have no hesitation to say that the solution phase research is dominant over solid state and gas phase. Probably the solid state research need high temperature, gas phase research need high temperature and high pressure, whereas solution phase research work at moderate temperature and pressure. Wherever you need mixing, stirring, pumping, transporting, the solution phase research gave an edge benefit. But the solution phase has a problem of volatility. So how to address that? Yeah, thank you. So how to address that, we will see. So today's my talk would be on how we can engineer the properties of our choice, not one property, not two property, the combination of properties of solvents which are benign, environmental friendly, and then useful for various processes. We will focus on sorption and extraction processes. Okay. Let me start. I'm from chemistry department. Already sir told in very much detail. We have 34 faculty working on 34 different cutting edge research areas. So I request when you have some time, go through our department website and see we have plenty of opportunities for BSMS, new program starting from next year. We have MSc through JAM, and we have PhD through GATE and other exam CSIR lectureships. And if you have already crossed PhD, look for postdoc. If you have already crossed for postdoc, look for faculty positions. So I request you to go through our website. And let me start thanking all this. So today I am standing in front of you and talking because of all these people. These people have been, who are in bold, already graduated, completed PhD, and they are abroad for postdoc or came back India for a faculty position. These other people are still working, and these are the collaborators in the institute, in the department, in India and abroad. And without money, nothing will happen. So there are plenty of funding agencies who gave a lot of money, and because of them, we could do some work and I could share with you. So I asked one of my students, 3 students together made this slide. I said, whatever we did in IIT Madras in last 15 years, can you put it in one slide? 15 years work in one slide. So this is what we do at IIT Madras. We looking for alternative solvents, so which are environmental friendly and we want to replace toxic solvents in industry and we want to tune the structure. So, tune the structure of alternative solvent. Why we want to tune? To get the targeted property, so the properties of our choice, be it a heat capacity or viscosity or conductivity or refractive index or surface tension. So we tune the structure of new solvents to achieve the targeted property, and why we do so? To have a targeted application. And this is what we do. Alternative solvents, we study their thermodynamic, phase equilibria, data analysis, and what is our application? Can we convert waste into wealth, W to W, or waste into commodity? And that's what we say. I said, no, one slide is also more. Can we put it in one equation? 15 years of research, can we put it in one equation? Then we come up, we work integrating fundamental science with engineering approach for the socially relevant and sustainable technological development. This is what we do. Let us take in. How many of you know this logo? Just raise your hand. I will not come and ask anyway. We are very far. How many of you know this logo? Nobody? This is United Nations Sustainable Development Goals logo, UNSDG logo. How many colors are there? Each color represents one goal. There are 17 colors. So 17 goals are there, and so UN has requested across the globe, all faculty, all researchers, all societies, that your research, whatever you are doing, please continue to do, but can you shift slightly which align with any of these goals? We will see few of them. What is a sustainable development? Industry should flourish, human life should become more and more easy to live, and still we should develop, and this development will be called sustainable development when this development is economically viable, environmentally acceptable, and socially equitable. We are looking for that kind of development. If you see the chemicals, every year plenty of chemicals are added. Now $5 trillion about chemicals, and this is going to be double by 2030. So we have a huge responsibility on us as a scientist. What we should do? We should use less stuffs and we should make less waste. We should not generate waste, or we should use waste to convert into products. So far, let's say if I purchase my mobile, I don't know where the raw material, where it has been made the part, where it is assembled. I only know the shop, I will go and buy. After 1 or 2 years, mobile is not working, I'll just buy back, or I just throw the mobile and this. What happened to that later on? We don't know. Now the new problems are coming is e-waste. How to address this? Now, this is a linear economy where chemical supply chain, product supply chain, and product life chain and global value chain, they don't care about other one. It's called linear economy. But now, if you go for a permission to any new companies, government will not give unless you show the circularity. So, starting from the raw material to production to consumption, waste management, recycle, you have to close the loop. This is the future, or this is the, already it's in the current, you have to work on circular economy. Any research field you do, please ensure that what are byproducts, are you wasting energy, are you generating unwanted things, or after using it, how you will put back. You have to close the loop, circle. So, lab to market, any research we do, why industry people don't believe us? We publish high impact journal, high paper, still they have their own R&D. Because errors and error analysis we don't do so thoroughly. So to go to lab to market, we have to think how it will be. Exaggerate. If I ask you how to measure density of water, I have water. How you will measure? Mass by volume. 10 ml you take and you weigh it 10 gram. So 10 gram divided by 10 ml. So 10 will cancel out. You say 1 gram per cc or 1 gram per centimeter cube. If I ask you what is the error in that, so your balance, let's say, has 0.01 gram error and your pipette has 0.01 ml error. So your mass is 10 plus or minus 0.01 divided by volume is 10 plus minus 0.001 or 01. So 10 cancel out. What about error? Will error cancel out? You have error in numerator and error in denominator. Will error cancel out? No. Error propagates. We say, I don't know in Tamil, but in Hindi we say, दुश्मन का दुश्मन दोस्त होता है. Enemy's enemy is friend. But error पे error cancel नहीं होता है. You have error in numerator and your error in denominator, it will not cancel out, it propagate. So we have to be ensure this. And when you go from lab scale, especially chemist works on milligrams to gram. If you go for biology people, they work in micrograms. Okay, chemist works in grams. Engineers works in kilograms. Okay, but when you go from lab scale to pilot scale to industrial scale, the scale expansion is multifold, and similarly error will also expand multifold. So one has to be extremely careful when you do lab scale research. So, and the nature works on the third law of Newton. Many physics people are there. You care for nature, and nature will care for you. You destroy nature, nature have no option than destroying you. And we are not powerful, or we are not at all powerful compared to the nature. So when nature shows its anger or her anger, you can see how it will happen. So we have to care for nature. We have plenty of varieties of the pollutions you have seen, and today we will focus on the solution-based waste. And you might have seen this movie. How many of you watched this movie? Okay. So today also I am going to talk about RRR. What is first R is for reduce, second R is for reuse, and the third R is for recycle. So can we reduce, reuse, and recycle? And this starts in our home. It's not about how much you can afford, it is about how much you can reuse. At home, let's say you have two boys, elder's boy's shirt becomes smaller, means the boy is growing. The shirt will be used for the younger one. And younger one is again growing, the shirt will not be thrown. It will be converted into vegetable bag or something. The bag got torn, it will not be thrown. It will be used as a wipe for the platform in the kitchen. Even if it become dirty, it will not be thrown. It will be used somewhere, wherever the rat is coming, you put as a packing material or whole. So it is there with us. So how many times you can reuse, and this concept we have to apply in research. Nothing is waste. Only thing we don't know how to use it. So that's how we have to see. So today's talk will be on little bit on alternative solvents, and then we see some applications. And as I told you, solvent play a major role. I said solid state research, you need high temperature, gas phase research, you need high pressure, and solution phase is better whenever you need in the industry level, mixing, stirring, pumping, dissolution, transporting. The solution phase is easy. Having said that, but the volatility is issue. They volatile. So this bring lot of problems. And how to address that? You have to replace. And while replacing, what are the challenges? You need different polarity, different basicity, and different protic and aprotic nature. So I ask many students, especially chemists, how you choose the solvent? They say, sir, it was available on the rack, so I took. That's a generic answer, probably may be true, but in a scientific way, then people start telling, sir, I see the boiling point, melting to boiling point or flash point range. I see functional group. I see whether they are polar or not. So is that adequate? Probably that is a starting point to know the polarity, functional group and temperature window, but that's not adequate. One must see when my research goes from my lab to the industry scale, whether this kind of solvents are available in large quantity, affordable in large quantity, or whether it has environmentally any impact. So this, in the beforehand itself, one has to think. Then only one can think of going. So anything you do a research, when you do a research, why do you do research? One student says, sir, I want a job, I want a degree, I want a name, I want a fame, I want a research article. All these are true. But if you see the big goal, you want to help the humankind, you want to help the industry, you want to have a bigger picture, so you are talking about large scale. So when you talk about large scale, at that scale it should be affordable and available. And then you see, you have to see the legal controls, environmental impact, health and safety impact. All this is available on the label itself, MSDS. How many people read when they purchase chemical? In most of the time in Viva I ask about, have you read MSDS? How much it cost? From what is the starting material, how it is made? Because you are working on that for 4 or 5 years and you don't know about it. If you put a Camlet top plot of different polarities versus basicity, this is for common solvents, industrially available solvent, and these are for benign solvent. For example, this region you don't have anything to replace this tetraalkyl ammonium. So we don't have a benign solvent to replace industrially important conventional solvent. So as a scientist, it's our duty to make more and more new solvents. This is ACS Green Chemistry Institute's website, where around 270 solvents have been screened with different algorithms like functional group, physical properties, safety. So you choose these parameters and it will give you which is the best fit out of 270, and then you can use that. It's free of charge. Then public-private partnership company Chem21 come up with some more solvents. They have divided most of the industrial important around 200 solvents into 6 categories based on their safety score, health score and all these things, and divided into families. Then you can see instead of this red, can you go to yellow or can you go to green? Then you can see within the family it will work or not. Of course, you have to see the flash points. All this is about looking towards sustainable solvents without compromising on your final product. And this is the table. But if you see the large scale industrially, plenty, thousands of solvents combinations are there. How to get this many formulations? So we need a large pool, and then people go close to the nature. Then they say, okay, don't use solvent. No solvent chemistry. Supercritical fluids. And then they say bio-derived solvents. All of them have their own research. So today, the automotive structure, construction sector and the energy sectors expanding so fast, they need large quantity of solvents. And due to stringent environmental regulations and policies, all of them are looking towards benign solvents. And largely now they are going towards bio. But today I am going to talk on something already known. I put there old wine in a new bottle. So molten salts known for ages. Anybody knows sodium chloride melting temperature? Sodium chloride, uppu? You call uppu only, no? In Telugu also uppu. Melting temperature, anybody knows? Physics, chemistry. Wrong answer is allowed. Shout something, some number you shout. 700, okay, wrong answer, no problem. 100 is wrong, Amma. 100 is completely wrong. Close to 800, okay? Okay. In sambar we put salt, okay, but the salt will not melt, it dissolves, okay? Anyway, we are talking about salts which are liquid at and around room temperature. So, Paul Walden discovered ionic liquids accidentally, ethyl ammonium nitrate. They used to call that as a liquid salt. And Ken Seddon is the one who started this field. I was fortunate to work with him when I was in Belfast during 2000. So this class of solvents possess combination of unique properties. Since they are made up of ions, they are having electrochemical window, and ionic and electrochemical window is around 3.5 volts. So for battery applications, supercapacitor applications, this will be one of the best solvents. And conductivity is high, vapor pressure is low. Above all, you have great varieties of the structure possible, because you have, in conventional salts, both are inorganic nature, cation and anion. Here, it's a hybrid salts. Your cation source is heterocyclic, anion source is conventional anions like chloride, halides, or tetrafluoroborate, hexafluorophosphate, and you see the size. Cations is large and bulky, anion is small, and you have alkyl chain length. So based on cation, anion and alkyl chain length, theoretically millions of ionic liquids possible. So you can formulate millions of new ionic liquids. But we have to see what is the predominant nature, why they are salt and liquid. So the thumb rule says, because of this large asymmetry in the size of the cation and anion, they cannot come closer and make solid. There are plenty of void volumes, and they cannot go far because they have interactions. So then they remain as a liquid. I'll take a glass of water, put salt in that, I stir it, and there are ions, and now it is in liquid state. Can I call ionic liquid? Answer is no. That is ionic solutions, where Na plus and Cl minus are surrounded by OH minus and H3O plus. It's called ionic solution. We are talking about ionic liquids. Their ions are surrounded by their own ions, cations by anion and vice versa. And that's the beauty. Because of that, they possess combination of several properties. Having said so great of this, is there any limitation in this field? There are two major limitations. One, they are expensive than the organic solvents. Two, when it is expensive, nobody will use. Industrial especially. They try to avoid. The second one is viscosity is higher. When viscosity is higher, what is the problem? You need more energy for uniform mixing, stirring, pumping, transporting. Energy more means again expensive. So how to tackle these two problems, like one stone, two fruits, what do you call something like ek tir do nishan. How to tackle both at a time is, don't use them completely, use them in small quantity as a performance additive. What you call as additive. That's what we will see it, okay? In this case, what happened when you use in smaller quantity, cost has been taken care, viscosity will not increase. When you say small quantity, what is a large quantity? It's a water or organic solvent. Then question remains same. Sir, in the 5 slides before you say you want to replace organic solvent. Now you say it's the same. How it is, both are true. So for a given final product's quantity and quality, can we reduce the requirement of organic solvent substantially? And that is where we say it's a greenness. We don't need to generate electricity. I just go pass by classrooms and I see fan and lights are on and nobody is there. I just go pass by and switch off the light and fan. I have generated electricity because I have saved that much. So this is the thumb rule. Lewis acidity of the cation source and Lewis basicity of the anion source is low, and the combination of this kind of cation and anion will be always in liquid state. So you have to focus, and this, when both are high, the resulting salt will be always solid. If it is mix and match, then you have to see for more in-depth analysis required whether it will be formed liquid or not. Since you have a choice of cation and anion and alkyl chain length, you can tune the polarity, you can tune the properties, you can tune the all of your choice. In mathematics, we study the probabilities. No, let's say I have 3 pairs of shoe, 5 pants, 6 shirts, 3 caps. How many varieties of the way I can dress? Probability you will find out. So as the number of options are more, probably the probabilities number of is increasing. So you have cations plenty, anions plenty, alkyl chain length plenty. How you can tune, accordingly you can see. Plenty of applications are there. Let me go. And it's not only on paper it is good. In reality also it is good. So there are plenty of industrial applications of this ionic liquid in last 20 years. We are going to focus now only on performance additive. What you will do, you will take in small quantities. You know bhajis, pakoda, when they made, they add that white powder, what do you call that? Soda. How much we add? A little bit pinch. But if you don't add and add, there is a huge change. Something like that, can we use them as a performance additive and then see the grind? So, despite this, lot of work has done on this, the thorough structural property understanding is still. So many researchers just arbitrarily took this anionic liquid, this solvent, that solvent, working, another paper working, not working, oh this is not working, another paper. So can we study systematically? This we say. And these accurate properties are very, very essential. Anything you do at the laboratory scale and you achieve excellent results, and you want this to go to the large scale, from laboratory to pilot to industrial scale, you need so many parameters as input parameters in the process and product design calculation. It's not like in the laboratory you try and say, oh you take this 1 gram, you take this one, oh the reaction fail, I see throw. In industrial scale you cannot take large reactor, oh it's fail, I see throw. You cannot, then your job is gone. You have to be extremely sure, 100% sure that this will happen. And you have to optimize. Optimum means what? Neither minimum nor maximum. That is the optimum. If my tank size is, let's say, 50,000 liter, so all the reactants, everything together should not cross 50,000. But if it is less than 50,000, that means some gap is there, you are not utilizing to the fullest potential. Temperature you are maintaining, pressure you are maintaining, catalyst you have added, time you are spending, salary you are paying, but the product you are making less. Nobody will appreciate. So we have to optimize to the highest possible level. But if it is spillover, you calculate 50,000 liters, but if it is spillover, then it's a problem. It may be accident, entire reactor will blast, again you will lose the job. So all these parameters are required in the process and product design calculations, and thermodynamic properties are extremely essential, without which you cannot scale up. So we have though there are plenty of companies selling, we have synthesized our own ionic liquid. The reason is synthesis is not very difficult. The difficult part is handling them. They are very hygroscopic. As soon as you open the vial or a bottle, they will take moisture. When they take moisture, or what will happen, especially which kind of property will alter fast? Transport properties alter. Viscosity and the conductivity will change huge. So, purifying them and handling them in dry condition is a challenge. We have synthesized plenty of ionic liquids, more than 100 new in 15 years, okay? More than 50 known ionic liquid. We have library of 150 ionic liquid, more than 50 deep eutectic solvent. So we synthesize new solvents. Why we synthesize, I will tell, okay? And then purify, characterize, and study their thorough thermophysical profiles. Acoustic properties, volumetric properties, transport properties, refractive properties, phase equilibria, everything as a function of temperature and pressure. So you can see the list: density, viscosity, speed of sound, heat capacity, surface tension, thermal conductivity, electrical conductivity, refractive index, compressibility, expansibility, all the we check all the properties. Yeah. And we study their solubility in varieties of the solvents, liquid-liquid equilibria, solid-liquid equilibria, vapor-liquid equilibria as a function of temperature, and few properties as a function of pressure. We generate large data bank. Why we do so? Why we do so? Let's say if you have so many ionic liquid possible, can we study all of them? No. What is the limitation? You can't study all of them. First thing, I don't have that much time. Two, I don't have that many resources. Human resource and the chemical resource. I don't have that much fund. Fellowship I have to give and the chemicals we have to buy. So with the limitation of time, resources, human resources and funds, we study systematically some families: cation common, anion changing. Anion common, cation changing, both common, alkyl chain length changing, and temperature. Then we have some data bank, and then we develop structure property correlation. If I want to ask you, let's say I want to mix ethanol and water. Ethanol and water. You know mole fraction. What is the range of mole fraction? Mole fraction. It is between 0 and 1. Okay, mole fraction cannot go beyond 1. Okay, between 0 and 1, how many numbers possible? Between 0 and 1, how many numbers possible? Mole fraction. I want to mix two liquids, both should be there, and mole fraction should be different. How many varieties of the glasses we can make? Between 0 and 1. Anybody would like to dare to answer? Infinite, right answer. Please clap for him. Between 0 and 1, infinite mole fractions are possible. This is, we are talking about only two liquids, binary mixtures. In industry, you have multi-components. Then the possibilities are infinite. Then how to do all these calculations? So we have to depend on computational techniques. We have to depend on structure property correlations. We have to depend on group contribution methods. We have to depend on equation of states. We have to depend on the modeling. And we do that by taking some data and develop the new models. So these are some of the instruments what we study or what we use. If you see, below everywhere we wrote accuracy. So in science, please remember, there is any research you have to express in numbers. What is quantitative? Science says nothing is wrong or right. But under given circumstances, it has to be reproducible. Okay? What kind of error may come? you study in analytical chemistry, instrumental error, calibration error, human error, and the highest error is due to sample purity. If sample itself is not pure, what we will do? So all errors are, so any number you put, you must mention your confidence level or the error in that, at what confidence level. By default, Excel gives 95% confidence level. Microsoft Excel. We are happy to announce more than 20,000 data of the new ionic liquids have been utilized in measured at IIT Madras, has been taken into this. Now I'll take you to few applications. Our expertise is to design, synthesize new solvents to have a targeted application, to get the desired properties set. Somebody says, hey, my application required polarity in this range, surface tension in this range, heat capacity in this range, this much is this. Can you make? I say, yes, we will make. And we'll check. Okay. So we'll see few application. We are chemist collaborating with petroleum engineer for this project, and the money is given by Oil India Limited somewhere in Assam. I am in chemistry department, collaborated with petroleum engineering department. Money is given by Oil India Limited, and student is with me. 35 lakh rupees they gave for 3 years. We got 3 papers, 2 patents, 1 PhD degree. 3 years. Okay. How unlike minds has to come together is essential. You want to go for a movie, picnic, party, go with like-minded people. You want to excel in science, discuss with unlike-minded people. Science grow with argument based on scientific justification. Science grow with criticism. Science grow with comments. So we have collaborated with engineers and company where we saw the tanks, these big tanks have settled the crude oil and it is not coming out. Conventionally people heat it, so outside they put heating coils, still it is not dissolving. Then they put surfactant kind of things, toluene, and best remedy is toluene. Toluene also not going, surfactant also not going, formulation, and the human has to go inside and dig, and suddenly somewhere you see hard surface and somewhere soft surface, entire human will sink. Very risky. But the companies do not want to throw this storage tanks because they are in good condition. So they come up with this, can you solve this problem? So 7% of resin is holding large amount of aliphatic and aromatic not to dissolve. So we started experiment. Take conventionally, toluene can dissolve, dodecan can dissolve this, okay? But we don't want to use that in large quantity. So what to do? So we took conventional solvent and added tank bottom sludge. Whatever is dissolved, we say it is 0 because we want to see the effect of ionic liquid. We add 0.1% by mass ionic liquid, and the bottom part where the dissolution is decreased, checked with IR and NMR. Top part where crude oil dissolved, checked with UV. So in UV, concentration of this carbon or aliphatic and aromatic should go up. In IR and NMR, it should go down. So 0 is after adding toluene or heptane or dodecan here, and these remaining numbers are after adding ionic liquid. So small quantity of ionic liquid, how much? 0.1% by mass can enhance the dissolution up to 65%. That's a wonder. But still, organic solvent is there. The requirement is gone down. So let's say earlier it was for 100 ml, you have 20 gram dissolving, now 20 plus 65% more. And this is a proof of concept by IR and by NMR and by UV. And probable mechanism is probably, we said how small quantity is doing wonder. We said one bulky guy sitting in the middle and holding two other students like this in his shoulder, not allowing. Tolvins or other students are pulling but not coming out. The ionic liquid go from the back and pinch here. So the middle guy got jerk and the remaining will say. This is a story I tell. But what is happening, the lone pair on sulfur or nitrogen or oxygen, all heteroatoms, it is attacked by ionic liquid. So this resin is no more holding aliphatic and aromatic stronger. So the toluene can take them out. This is the beauty. Well, we also worked on enhanced oil recovery. The crude oil coming from the earth, naturally it comes, it's called primary flooding, and then they at designated places they put hot water or steam, that is secondary flooding. But now we are talking about tertiary flooding. Here you have a bath of 100 gram silica of uniform size. You push from here and then you collect here. Then we see, so conventionally varieties of the solvent we have tried 100 ml, the maximum we got is 52, means 100 ml crude oil you pass, whatever you do with just simple pushing and the second time 100 ml hot water at this temperature, both together you are not getting up to 52. So 48% is still crude oil is inside. Now what we did, the second time pushing, instead of only this formulation, add 10,000 ppm of ionic liquid, 52 becomes 72. So 20% extra crude oil is coming. And the reason is, when you add small amount of ionic liquid, the interfacial tension between water and crude has been decreased, or the tension between rock and the contact angle between rock and crude has been better. So it can be washed out easily with the steam or hot water. We have worked on IGCAR, Kalpakam with extracting lanthanides and actinides and high level liquid waste. And if you see, they trap these radioactive materials in very small quantities. Disposing is a challenge. Where they dispose, you will be surprised to know. They put in big tankers, and these tankers has to be buried in the sea somewhere, and they have to calculate that even for hundreds of years, it is no harm here burying. Large ships will not come or large sharks will not come and nobody will damage this. It's very challenging. So can we replace, it's a large quantity of nitric acid solution and trapped with small amount of radioactive materials. So we have extracted that threefold. Instead of conventional these digloclamides, when you add ionic liquid, so instead of 3 tankers filling, you can fill it in 1 tanker. It's not about reusing radioactive material, but you are reducing the liquid quantity or nitric acid quantity required to this one. Okay. We have worked on vapor absorption refrigeration system. This is with mechanical engineering. So earlier was with chemist, and before that was petroleum engineers, and this is now with mechanical engineer. What we want? We want to run vapor absorption refrigeration system where you trap ammonia or other things in the conventional solvent and you heat it through sunlight and then you run the refrigerant system. The challenge was the size of the equipment is very high, and we showed we can use them as a performance additive. Add some water, you need not to take, and you can run the vapor refrigerant systems. We work on polarity of the solvent. We work on varieties of the structure property correlation, and this is the competition of who is having large polarity. So far we studied the alcohols or the water is the best polar solvent, but we can tune the structure to make further. This is a comparative method, polarity increasing. And all of us know our engines or the what you call the trucks, today the transport goes through so many states on the same day, and the temperature change variation. Somewhere it will be very warm, sunlight is very high, somewhere it is raining, and somewhere it is very cold. So when engine pass through these varieties of the things, how it sustain the adaptability, or the truck is running continuously for 10-15 hours. So what could be the properties of the engine oil should be, and they are making, if it is more carbon, and immediately the engine oil will not sustain longer. So we also worked on this kind of, this is the conventional therminol, improving their heat storage density and everything better. All the properties we got better than the conventional engine oils except the viscosity. We need to address this also, or we can use this as an additive to our existing engine oils to increase their performance much better. Electrolytes in dye-sensitized solar cells, where if you see the solar cell, it has a solvent. In the during daytime it expands a lot, and night it will contrast. In this process, continuous process, this is the predominant reason for leakage. So we need a solvent where expansion is less. If I ask you in thermometer you have seen in hospital, thermometer, what is inside? Why mercury only? Why not ethanol thermometer, acetone thermometer, water thermometer? Why mercury? Anybody? The alpha or expansion coefficient is uniform between 0 and 100 degrees Celsius. Whether you increase 1 degree from 5 to 6 degrees Celsius, or 26 to 27 degrees Celsius, or 92 to 93 degrees Celsius, the expansion of mercury is uniform. So you can just put lines and then you can measure, which is not the case for others. There are other thermometers other than mercury, but in different range. We have worked on ionic liquid having uniform expansibility, can be used as a thermometer but in a different temperature range. Well, we also worked on varieties of the biological waste. Today if you go and see fruit market or vegetable market, you see so much waste is happening. Or you go to any restaurant in the evening at about to close, so much waste is still there. So can we address this? How we can address or biological waste or the other one? So we tried aqueous biphasic system where both the phase are water rich. One is added conventional salts, other is added sustainable salt, and due to the polarity difference they are phase separating, and in one phase you take the waste and convert it into, extract into other phase, no extra energy, only stirring and allowing to separate, and partitioning is happening, physical separation, and you have to put this in a continuous process in several cycles. Can you extract this? And if it is possible, that would be great. So we checked various phase forming component like monocationic, dicationic, zwitterionic to extract amino acids, alkaloids, lipids, dyes, metallines, pharmaceutical compound from one phase to other phase. So most of the industries, whether it is cosmetic or pharmaceutical, when they discharge final liquid to the canals or rivers or sea, it contains trace amount of these materials and it damages the aquatic environment. So before they discard, can we do this liquid-liquid equilibria not to get that metals or dyes, but to make the water purified, so the same water can be used in the industry and we can achieve ZLD, zero liquid discharge. Well, we have tried tryptophan, caffeine and varieties of the things. I am not going into, and we also worked on desulfurization of the fuel, sulfur and all these things. And today's buzzing word is carbon dioxide. Anybody knows what is the best solvent industrially to carbon dioxide sequestration? Alkanol amines. No industry could dare to replace that because the alkanol amines are dead cheap And what is the challenging part? Regeneration is a challenging part. You need a lot of energy to get the alkanol amines back. So we are looking for a solvent not to only adsorb, but desorption should be energy efficient or economic. This is the challenging part. And we tried with varieties of the mixtures. We worked with electrochemists to use them as an electrolytes, supercapacitor, sensing purpose. And you see how many applications we started, because any application you see you need solvent. Even nano chemistry people also tried when you want to have a desired size or uniform size. Can we have this solvent? Answer is yes. You tune. And biomass, the nature is so great, the outer layer breaking itself is a problem. The first layer breaking is itself is a challenging. And then once you go, you can go for pre-treatment. We have taken rice straw, wheat straw, and we have hemicellulose and all these things bacon. And now we tried micropollutants. We say microplastic and micropollutants is a now buzzword again. So they are very small size. They are waste from pharmaceutical companies or cosmetic companies or dye industries. And this, can we extract liquid? We could, because we have designed this kind of new solvents and extracted. We have tried pharmaceutical compounds also, N-methylpyridine or methylpyridine and other things. We tried deep eutectic solvents, new solvents. I know I am going fast, but I will tell you, take home message. You never saw here anywhere hi-fi instruments. All are just UV, NMR, isn't it, IR, and liquid extraction and the thermophysical property measurements. Okay? We have done some computational studies to understand the DES and all this, how you are calculating. And then last work let me present. Today, e-waste is the biggest challenge. Batteries and boards, motherboards and all this, what will happen to them? So many people are throwing computers. Can we generate precious metals again back? So we took spent lithium ion batteries, cathode material, and tried to get, this is the step I am talking. E-waste you generate and dismantle it, physical separation is open, and then you have to do leach. Leaching agent should have reducibility, acidity, hydrophilicity and complexing ability. And you see that in lithium ion battery, cathode material is about 41%. Can you get metals back? So we tried taking lithium and cobalt using deep eutectic solvent, and this is the real batteries or the spent ion batteries we used. We separated cathode material, we took, we cleaned it, we take this LiCOO2 and both Li and cobalt in oxalate form, and both of them are highly pure compound. We check with TGA and SEM and 99% pure, we got the both. Now we are thinking, can we put back this and make new battery? So the cycle will be, and how much energy we are spending. Is it worth buying new battery or reusing this battery? In industrial, so far they are using hydrothermal and metallurgical, just to throw, dump and heat it. And to dissolve also they use aquaregia, which is harsh condition, high temperature, which is harsh, energy intensive. That's why people are not reusing. You know, last Olympics, all the medals were made from the metals recycled using the e-waste in Tokyo Olympics. And they spent more money than buying a new metal. They say it's okay. Japan said it's no problem. Slightly costly than buying new gold, new silver, no problem. But we will extract everything. So this is why, but now the challenge is environmentally benign, no harsh condition and economically viable we have to make. So that's where we are looking. So and this recently published as a cover art, it's only one student did everything, Baiju. This is a cover page article in ACS, August 2024, this paper has been published. So overall, in this sustainable solvent or applications, what I try to explain, one, you can have new solvents with the properties of your desire. You can find a hero which can do comedy well, which can act well, which can do fight well, which can do dance well. Means having the properties of your choice. Second, to do a wonders, you need not to have hi-fi instruments and the great collaboration. What you need, unlike minds has to come together, scientists and engineers has to come together and think, and fundamental science is very, 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 very essential for the technological development. You don't need hi-fi instrument. If it is there, it will help. But even if it is not there, you can do wonders. So coming back to this kind of solvents, I did a SWOT analysis. This is the last slide. What is the strength? You can tune the property. You can check what kind of cation you want, what kind of anion you want, what kind of chain length you want. So if your main sources are benign, your resulting would be benign. What is the weakness? Still they are expensive. They are viscous. But both the problems can be addressed. Don't replace organic solvent completely, but use this solvent as an additive. Without compromise on final product's quantity and quality, you reduce the organic solvent requirement. What is an opportunity? You can enhance the sustainability, you can make process better, you can close the loop with the circular economy, and you can convince the environmental policy makers and the industry that yes, this is better. What is the threat? How many times you can reuse before going to the use? This is where now it's challenging. People are working more and more, because what is the business funda? Minimum investment, maximum profit. What is the science funda? Minimum energy requirement, maximum product, or highest pure product, no byproduct. So we are working on that. So the last stage on the recovery and reusability. So I tried to explain varieties of the properties and so many applications. And I believe humankind in the long run will always need energy, environment, water, food and health. So whatever research you are doing, if it is aligned with this, any of this, it has a great future. But along with this, ensure sustainability so it can go long run. Remember, reduce, reuse and recycle. And remember, fundamental science or basic science is the foundation. It is essential part of any technological development and innovations. And plenty of ions are there. Theoretically, you can make millions of ionic liquid possible. And the last message before thank you slide. Anybody can read this. What is this ionic liquid? Any student can read what ionic liquid it is. It is not ionic liquid, it's a message. Research, in research one can find alternative to anything. If not anything, I am sure for many things. When you are, be positive, no negative. Thank you. I am ready to take questions, suggestions, comments, clarifications. Anyone? Loud. Yes, that's what I put it in the thread. We try to purify instead of, see, so many people are struggling to purify before put back. But don't do that. Don't purify, but can you close the loop for the second cycle, third cycle? So keep on feeding what is your raw material or the materials or the waste material. You separate it and this put back for the second cycle. Keep this and you maybe keep on topping up for the as many cycles as possible. And there is a stage comes, the reactivity goes further down, then you have to purify. It is energy intensive, but it depends on the process. This is challenging. That's where the cost is going up. We are looking for how to put the cost down. Otherwise, industry will not buy. Do we buy if we have, let's say you are buying a purse. If you want for a brand, you will go for Gucci. If brand doesn't matter, you will go for a better one, cheaper one. We all know there is nothing called cheap and best. If it is cheap, it is not best. If it is best, it is not cheap. But still we try to compromise with this. So all about money, all about cost. Any more questions? Clarifications? Comments? No. So if no questions, you please feel free to write to me. I'll just put home. Yeah, my email ID is there, gardas@iitm.ac.in. So you can drop me email anytime if you want. And if I don't reply, second time you write, sir, that day on stage you told you will reply, you are not replying. So second time I will reply. Thank you.
Thank you, sir. We are deeply grateful to Dr. Ramesh L. Gaddas for his enlightening keynote address, which shed new light on the latest advancements in his field. His expertise and passion for research have inspired our delegates, and we appreciate his valuable contribution to our conference. Thank you, sir. Okay. We are pleased to resume our conference with technical session 6, focusing on supercapacitors, design and computational method. It is our honor to have Dr. D. Manigandan, Associate Professor from the PG and Research Department of Physics at Aringer Anna Government Arts College, Viluppuram, Tamil Nadu, as our chairperson for this session. Dr. D. Manigandan, research expert, spans solid-state physics, condensed matter physics and computational physics. His impressive academic record includes 21 publications in reputed journals and over 441 citations. We now invite Dr. D. Manigandan to introduce our next speaker, Dr. Venkatesan, by sharing his profile with us. Before that, I would request Professor Karthikeyan, Department of Chemistry, to honor Dr. D. Manigandan.
Very happy morning to one and all. First of all, hello. A very happy morning to one and all present here for the second day's session of this August occasion. Actually, I was to introduce the first person, but I was a little late. I got entangled in this traffic jam. But I could also, I think that I can express that review or thanks for Mr. Ramesh Gaddas. It was a very informative and interesting lecture, well delivered, and that shows his richness and depth of his knowledge in that subject with parallel analogies relating to real life, like what a beat, old wine in a new bottle, or single stone to mangoes examples, whatever. So thank you very much, sir, for your informative, interesting lecture on thermodynamics and chemistry. That is, even non-chemistry students could understand his lecture. And now I am here to introduce Professor Dr. Venkatesan. I know him for the past 25 years. My first UV spectrum of optical properties, that is absorption spectrum of my sample, first sample, that is copper nanoclusters embedded in glass matrix, was recorded in his lab, and the most sweetest, down to earth and an academician, that is highest academician of knowledge I ever seen. As soon as I just met him and asked for the help to record a UV spectrum, without hesitant, he just told me, okay, just use my lab. You know, I really recorded some more than 70 or 80, nearly or even 100 spectra for all my entire work of UV spectrum. Even in 1999 itself, he had a UV spectrum with fiber optic cable. That was normal spectrum. You keep the sample, reference or whatever it is, and you just wait for the scanning to happen from UV visible region. But what the spectrum photometer he had at the time was, you keep the sample and you see the spectrum the next second. And that was he, at the time in 2000 itself. Thank you very much, sir. I take this platform to thank you very much. And now I would like to introduce Professor Venkatesan. He is a professor in the Department of Chemistry, School of Physical, Chemical and Applied Sciences at Pondicherry University. And he did his PhD at the Indian Institute of Technology, Mumbai in 1992. And he has guided 6 PhD students and successfully completed 8 research projects. He has more than 91 research papers and 160, that is 1698 is the citation, reflecting his impact on scientific community. He had achieved an H index of 22, underscoring the significance of his research. With over 28 years of teaching experience, he has actively involved in educating students at various levels, from foundational chemistry courses to advanced subjects. His teaching includes topics like equilibrium, statistical and non-equilibrium thermodynamics, chemical kinetics, spectroscopy, analytical techniques. His commitment to integrating technology into classroom enhances the learning experiences of his students. Actually, he joined the university in the 2000, Pondicherry University, and rose to the position of an associate professor and was promoted to professor in the year 2018. His research contributions in advanced fields of energy materials, photochemistry, and his dedication to education ensures that he has a vital contribution to both the students' growth and to the scientific community. With these few words of introduction, I would like to invite Professor Venkatesan to deliver his lecture.
I would request Dr. Manikandan sir to honor Dr. Venkatesan sir. Thank you, sir.
Very good morning to all of you. It's nice to be in this beautiful hall, in this beautiful campus. After a wonderful lecture by Professor Ramesh, in fact, whatever we do in this particular case of research domain, we will use all the principles whatever Professor Ramesh has expressed over that. And my talk, I will not be focusing what we do, what is our output or something like this. I will have a overview of the energy materials, okay, especially one specific material called the supercapacitors. That's what I'll be talking about it. In fact, an overview of this particular one from the literature. And then finally that I'll be just telling you that what are the possible systems we are working on at the fag end of this one. In fact, my talk will be as two parts. One, what are the processes? I mean, what are these supercapacitors and how do they work about it, and how do you one go about in undertaking a research on that? And what are the kind of variables I should now look into this, how to now address all those variables, and how people have worked on this particular one. And the second part, I'll be talking about it, how do we now start doing a research with so much of data available? You'll be seeing the kind of data available in the literature is so enormous. It's not easy to start a new sample or a new product to undertake research onto this one. So I'll be talking about how do we go about computationally handle this huge data, and how do we start working at any institute level. It can be in this college or it could be any of this research, any institute research level. So the first part I'll be talking about the supercapacitors, and the second part will be on the computational part of it. Please let me know what time I should stop, because this other guy is joining at 12:15 or something online. So just let me know about 5 minutes in advance, okay? Yeah, let me start about it. I'll just, to start differentiating, we have two energy devices. Okay, energy devices which has been well documented in the literature from the very old days. The one which is the battery, the second one is the capacitors. In fact, both are being used for a very, very long period. Okay, right from when Daniel came up with this battery over here, we have been working on this one, and the physicists know about these capacitors for probably over hundreds of years. Very, very simple to do about it. If you look at the capacitor, I have two plates. I have two metal plates over here, and then I have a dielectric medium in between. It could be anything. It could be any of the material can be used, right from the very simple liquids to a very expensive materials can be used. In fact, one of the materials which has been widely used is ionic liquid, as he pointed out over there. And all we have to do is only when you charge it, when you apply a voltage in between the two plates, obviously the dielectric material actually orients itself, okay, orient itself into the positive and the negative electrode. Because of the orientation, this have a higher energy, okay, because it's oriented. If we don't apply this voltage, if we don't do this work, obviously they are all randomly oriented, these dielectrics. When I apply the voltage, I have this dielectrics orienting itself. When it orients itself, when I connect a load, obviously this destabilizes itself. Yeah, thank you very much, sir. It reverts back to the random orientation, okay, and it is oriented, and then when it's reorienting, obviously I get the energy out of it, and that energy is being used. That's what the capacitors actually been working on this one. We'll come to that. And in the battery, and obviously it is, it's a Faraday, there is an electron transfer is happening, there is a reaction is happening at the cathode, there is a reaction is happening in the anode. There are electron transfers happening at the cathode and the anodes over here, whether charging, discharging. Because the electrons are being transported across the materials, I can catch those electrons into the load, I can make it to work. Okay. Now both produce energy for me to do about it. Okay. I can start loading a load on the capacitor or in the battery. Doesn't matter about it. I can still run my machine straight away. But what's the problem? I don't know whether you can clearly read. I myself couldn't read much about it. Anyhow, I'll let you know about it. But there is a problem onto this between these two materials. There is a vast difference. Both can be used as an energy source, but I cannot use both for a very similar purposes. I cannot do it. Let's say, for example, let's say I start a fan. Okay, just put on a fan. You must have seen a small capacitor sitting over here, maybe about 20 microfarad or something like this, 20 or 30 microfarads or something like this. What do we require that? Obviously, to start the motor, I need a larger power. I need a more work to be done on this one, which I need to do it as a burst so that it starts rotating. Once if it starts rotating, to run the show, that I don't need to do much about the work. So to start the work, obviously I need to have a large power. Okay. To run the show, I don't need to have a larger power. I need to sustain that particular power. So to start, I need a large power. To run, I don't need a large power. I need to sustain a power. Obviously, to have a large power, you need to have a device which can instantly give a large output. And then for a device to run for a long period of a time, it needs to have a device where it can sustain this energy for a long period of a time. So you have two different options. Let's now translate to the electrical vehicles now. Now to start an electrical vehicle, let's say, forget about the scooter, they are much smaller motors. Let's say I want to start a motor in a four-wheeler, okay, in a four-wheeler car over here. The power requirements over here for that particular one is close to about 6 to 8 watts. Okay, 6 to 8 watts of that instance when you start that engine. Now, when you drain about 6 to 8 watts, the power from the battery, whatever the battery you have installed over here, the running distance becomes very, very small. So that's how, even though the car manufacturers say that you have about 200 kilometers of a range of running and all those things, it oddly runs for 200 kilometers because when you put off and put on the engine every time, there is a huge discharge in the battery over here. Now, how to get away from that? Obviously, presently we don't have much of an option to do about it. So when I compare the battery and the other things, let's say look at it. When I look at the battery over here, the charge roughly about the energy storage is about in watts per hour of energy. Huge energy is being stored over here. Okay, huge energy is stored, and then that's for hours. That means I can run it for a very long period. Okay. On the other hand, if I look at energy storage in the capacitors over here, it's watts per second. So that means if when I remove it, instantly it gets discharged over here. I don't have much power to do about it. But that's not the story. Look at the lifetime. The lifetime of your batteries. I'm talking about the lithium-ion batteries over here. The lithium-ion batteries is roughly about 1,000 cycles or 2,000 cycles. If it is a polymer, probably it can go up to 3,000 cycles or something like this. On the other hand, if I'm looking at capacitors, the capacitors goes about a few hundreds of thousands of times. So that means I can make 150,000 cycles, I can make it without degradation. Obviously, I can also do with this one, but it will have a lot of degradation. And that's the reason most of our mobile phones batteries don't long more than 3 years. 3 years, 4 years. If your longer period in your WhatsApp and other your social activities, obviously your lifetime is going to be much smaller because draining is larger. Okay, so the rate at which you drain it is also larger over here. That one part. The next one, look at the cell voltage. The lithium, obviously, you cannot have anything better than lithium because that's the highest voltage you can get it in the what is available in the nature. So you can have maximum up to 4 volts. I'll come to this. It can be extended up to 5.5 volts. I will come to that one. And then that's the voltage you can do it. But the way I can do it over here in the capacitors, it can be anywhere all the way up to 800 volts. That means I can have a huge work is possible on this capacitor over here. And the specific energies are going to be much different over here. The major problem is the cycle cell. Okay, the cycle cells are excellent in capacitors. Cycle cell is very poor in batteries, but the energy density could be larger for a long period in the battery, but a very short for this particular one. So when I want to really have any energy materials, I should be looking at the energy storage, what kind of a cell voltage I'll be looking at it, and then what could be the specific energy that will be coming out of the system, what could be the specific power, and what could be the cycle life. Now if I start any energy material, I should be very, very careful with this particular one. In addition to this, I need to worry about it, the materials I use in all those systems. Let me just go a little bit again. Okay, just introduce briefly again. What do we need this? Obviously, I need to have a new energy storage devices. I need to have a very high power density. I need to have it, and then I need to have a long life cycle. Now, these are all my requirements as it is. Have we actually gone through this? No, we are not really going through this, but we have been very, very close to this particular one. All right. So that means my supercapacitor, whatever the things I'm looking at it, that should now bridge the gap between the conventional capacitors, okay, which is easy to do about it. And then we need to have, and the bridge, the battery is the other side, where we need to have a sustained power output. That's the two things. I need to get a huge power at a very short time period, and also I should have a very long sustainable output. So these are the two things I need to really worry about it, and then how I can use it onto these vehicles. Generally, if I want to start my work on a capacitor or supercapacitor on materials chemistry, especially in the energy storage, one of the immediate information I get it is what is called Ragon plots. This is what is called a Ragon plots. In fact, which describes about the power density. That means how much of a power I can get it. Of course, this is gravimetric power density I have written it over here. It's how much of a power I get it per kilogram, and how much of an energy output I can get it over here. Look at the batteries. Look at the batteries over here. That's where the present batteries. Huge energy density. I have a huge energies available in this. But the amount of the power I can draw from it is very, very small. It's about 1 order, that's all. I don't get more than that, okay? So I cannot draw a huge power from a battery for a short period of a time, in a short period of a time. On the other hand, look at the electrolytic capacitors and the supercapacitors somewhere in between. Now the electrolytic capacitor is far away removed from here. I have a very low energy density, but I have a huge power density. So I can be very easy to draw a huge power out of it, but I have a very low energy density, so I cannot sustain it for a very long period. Now I do have some material. If we can bridge these two gaps, that's where my supercapacitors. That means I need to integrate the chemistry of the batteries and the mechanism of these capacitors to build a new kind of a capacitor, which are now termed as in a colloquial sense called supercapacitors. That's my job. So I need to bridge these two mechanisms together. Okay, just do about it. I think probably, this probably will be a better one. Maybe okay, I'll just start from, I don't know whether you can really read this or not. I myself find it very difficult. Now conventionally, this is how the experiments are done. I need to have either I have a 3 electrode system. I will come to all those things. I'll have a 3 electrode systems conventionally. All I have a 2 electrode system. These are all experiment I need to do about it. So remember, in a conventional capacitor, I have 2 plates which are electrodes over here, and then I have a dielectric material in between these two things. Exactly like that I have it. Only thing is the kind of a mechanism I'm going to introduce over here, the supercapacitors, are slightly different. And what do I have it in this? And I have this is I'll come to this two things. Okay, what I have is the supercapacitor. I'll just talk about it. I do have a two plates. Okay, I do have a two plates sitting over here, and then I have a separator because I don't want to have a simple capacitance to build up over here. I need to bring remember, my job is to integrate the mechanism of a battery and the mechanism of the capacitor together. So in one of the electrode, I will build the battery either here or here, doesn't matter, it's all same to me. Okay, I'll talk about this one. So I need to bring a battery over here. What is a battery? So I have an example over here, which is the manganese in the 4+ oxidation state, MnO2, and then which goes to the Mn3+, which is a peroxide. Okay, so I have one electron reduction process is happening over here. So I have a battery now operating. I have a battery. Now on this other side over here, I have a plate which is now accumulated a positive charge. Because I have a positive charge, I have a negative MnO2 minus will be over here. Okay, so that means I have a capacitor is built on the right side of this diagram, and I have a battery, an electron transfer or a Faraday process is happening on the left side of this one. So I have now integrated the battery part and the capacitor part over here in a single unit over here, and this is generally called a pseudocapacitor, or it is called a supercapacitor, or it's also called a AA capacitor. So that means if I bring this capacitor in both the plates like this, becomes a AA capacitor. Okay, so that means I have now brought in a battery part, I have brought in a capacitor part. So I have brought in both. So this side of my device should give a huge power density, okay, and this side should give me a huge energy density. So that means all I have is now integrated two systems into a single system, which are colloquially called supercapacitors. That's what it's essentially it's happening into this particular domain. Okay, let's now look into this how the storage is actually happening in both these cases. This is the conventional battery, very simple. That means I have the cathode over here, I have an anode over here, and then I do have my conventional, I'm talking about a conventional lithium batteries, lithium cobalt oxide over here, and then I have a graphite sheets over here where the lithium can be intercalated, blah blah, everything. I have a charge, discharge, things are happening. So that's how the conventional batteries will operate, and that's how the conventional capacitor will operate, and that's how my supercapacitor to do it. I have now integrated this electron transfer over here, and also I do have a capacitance built up on this electrode. So I have both these integrated into one unit over here. This side should give me a burst of power, and this side of this device should give me a long standing or a very slow output, or a huge energy output can be possible onto this particular one. So I now bridged both these things. So my job to devise such kind of devices, what kind of materials I should use it over here, what kind of an electrolyte should I be doing it, and what kind of an anodes material I could do it about it. Okay, so that's the whole research. What is the whole process of research? That's what's going to happen. Okay, now let's just look at it. Let's say I have a device. I have a device which is a pseudocapacitor. That means I do have a batteries one side and do have a charge accumulation on the other side. I just want to do about it. When I do, I do have a different kind of producing this kind of an energy. Okay, let's just start. Let's say remember in a pseudocapacitor I have an electron transfer is happening, I have a charge accumulation is happening. That's how it's happening. So I have an electron transfer is happening over here. Okay, and then I do have a charge accumulation up here. So when I want to do both the process, I need to have an appropriate input to this. So this input can be now done at different levels. One, which is called an under potential deposition. Remember, I need to have an electron transfer. So in order to have an electron transfer, I can go with the redox potential which is available for a given couple, let's say lead plus, or a manganese 2 plus, or a manganese 3 plus. I can use that specific redox potential to deposit the metals on the surface so that I have a couple now starts building. Okay, so I can use, this is what is called an under potential deposition. That means I use the redox potential of that specific ion couple in order to do this deposition. This one is the redox pseudocapacitance. That means I use a potential which is not exactly the redox potential. Probably it is slightly lower or slightly higher than this potential. If I do the higher potential, then it will be depositing the metal on the surface, but it brings the ions closer to the electrode surface. Okay, so I bring it closer to the electrode surface, not exactly depositing like this. On the other hand, I do have a different kind of a potential where these ions are actually intercalating within the electrode surface. So I need to define this electrode surface in such a way where these ions are intercalated, not deposited, not close to this. This is the best option possible. This is the least option possible. This is how I can become an intermediate. This is now immobilized because it is closer to the electrode surface, but it's not as diffused like this. So the best option is to bring about this kind of a system where the active species is now very close to the electrode surface, bound to the electrode surface, not like this, but something like this, but it is still very close to this one. So I have now trying to achieve the best of both the ends. It is easy to remove, it is easy to put in back over here. So I don't need a huge power like this. I don't need to do a huge work to do like this, and it will not be as diffused like this. So my best option is to go for this. But how do I achieve about it? That's what the whole research is about on pseudocapacitance. Okay. Now, in order to do that, there are some typical models which are all there in all the textbooks over here. If you are in an electrochemistry, you already must be knowing about it. It's a well-known things. This is how it's Helmholtz model over here, and that one is going to be the diffuse model, and this one is a combination of both these things where you have an inner Helmholtz plane, outer Helmholtz plane. So, if we can really look at it, this is the kind of mechanism that's really happening here or here. Okay, I need to bring about. I need to bring this as effectively as possible. Remember, it is much easier than said. What I'm looking at is the distance. What could be the distance of this Helmholtz plane if you are aware from chemistry? What is the rough length of this Helmholtz planes? Any idea? It must be known for electrochemistry. You have electrochemistry in your course? It should be there because I was there, one of the academic council members. I should be knowing about it. It's roughly about a few hundreds of nanometers. Okay. If you have a very strong solution, it's going to be about 200 nanometers. That's all. So look at it. I am trying to influence the whole mechanism or the energy materials in this 200 nanometer length. Anything farther than 200 nanometer, it's no use to me. It's all going to be the bulk of the system. So I'm just looking at 200 nanometers of length from that electrode surface over here, and so the volume elements are going to be very, very small for me to do about it. How do I go about it? Okay. Before I start looking at the different kinds of materials I use it for capacitors, supercapacitors, or pseudocapacitants, these are all the conventional relations which are well known to any physicist or any chemist, any basic sciences. It should be there right from your higher secondary. So one of the things is capacitance. That's what we measure it, and that will tell you whether how good the material is all about it. I need to maximize this. I need to have what is called the specific conductance for a given system, for the given volume or the given mass. I have an energy density I need to measure about it. I need to have a power density. I need to have a Coulombic efficiency that tells you that how efficient it is between the charge and the discharge. So that will show you the lifetime of the material over here. Once if I have all these things, I can have a gravimetric reference, I can have a volumetric measurement of all these informations, or I can have an area measurement. So obviously, I can have a gravimetric energy density, I can have a volumetric energy density, or I can have an area energy density. I can have all those things are possible over here. But industrially, I need to have an additional things like this capacitance will be treated slightly different than from an experiment over here, which is done from the simple charge discharge cycle. Okay, it's slightly they have a different way of measuring it. That's the only difference. But the same things will be happening over here. But what we don't really do is this equivalent circuit resistance that I should be very, very careful so that the material is highly conducting. It's going to be easy for me to do about it. So I need to have a equivalent circuit resistance is measured, equivalent distributed resistance. Not only the equivalent circuit resistance, that means at different parts. Let's say for example, if I look at this material, I may have a resistance here in this material. I may have a resistance at the surface, I may have the resistance at the interface, I may have a resistance at both the sides of the separator, I may have a resistance on the other side of it. Similarly, other sides, I have a multiple resistances starts coming out within the system. But overall, there could be a different kind of a resistance can be there. Need not be resistance, need not be always linear. Okay, it need not be always a series throughout my system. So I need to be really worry about it, the equivalent resistances and how these resistances are distributed by system. As the systems become bigger and bigger and bigger, obviously this resistance is the way the resistance builds up into the system or become very, very complex. Okay, it's not going to be easy to distribute, easy to identify these kind of things. So once if I prepare any sample, I need to measure these are the things. These are the measurement I need to prepare about it. Okay. I now venture into a capacitor. That means all I need to have is 2 electrodes. I need to have it. I'll take some 2 electrodes. I need to have some material which is supposed to undergo a redox process. I know that I can take a chemistry book. I can take an electrochemistry book. I can use any of those materials over here. On the other side, I need to have some kind of an electrolytes. All I pick it. I know that I can start with the electrolytes. Simply like, let's say, I want to do a sodium. I want to do with the sodium. I take a sodium salt. I want to do with an aluminum. I take an aluminum salt. If I want to take a magnesium, I'll take a magnesium salt. That's it. So I start with something. Okay. Now, when I start looking at this one, I need to have, there are multiple variables or that. 5 minutes? That's all. Is it, what's the time now? 12 o'clock. I'll take 7-8 minutes or 12, okay. I need to have a lot of variables. The variables or something like this, what could be the nature of the binder I'm going to use it about it, the nature of the electrolytes in between, the device patterning, and then I need to have the separator, the nature of the separator, the nature of the sealants I'm going to do it, nature of the current collectors, and then I have the electrode materials. I have a lot of variables available. So these variables have to be looked at each one of that. I need to have the shape, morphology, what could be the size of the electrode, what could be the weight of the electrodes I need to take, what should be the concentration, all those things have to be there are a lot of variables available in this particular system. Okay. If I want to prepare it, then I need to really worry about it. If I want to have a supercapacitor, then I have an electrical double layer capacitor. That means I need to have 2 capacitance built in 2 electrodes over here. And then I have another one which is called a hybrid capacitors. That means I need to merge multiple mechanisms over here. And then I have a pseudo capacitor where you have a battery and the capacitance built. When I'm looking at the electric double layer capacitor, then I need to have a different kind of a materials I can take. I can take an activated carbon, I can take a carbon fibers, graphene oxide, carbon nanotubes, I can have a carbon aerogel, hybrid supercapacitor, I can have a symmetric or have an asymmetric, I can have a carbon, I can have a composite material, I can have a battery hybrid, I can have all sort of materials possible. Pseudo capacitor, I can have a conducting polymer, metal oxides. So I have a host of systems are available. If we take a specific things, so that means I work on this one. If I take a metal oxide, that means I undergo a redox potentials over redox reactions over here. So that will fall under the pseudo capacitor. When I'm looking at the electric double layer capacitor, that means I build a capacitance on the two electrode surface. So it falls onto this domain of pseudo capacitors. Right. The first thing is, okay, I can take any damn electrodes. The first problem is the electrolytes. That's where the problem really comes over here. When I talk about electrolytes, aqueous electrolytes are the best option because it has the highest conductivity, it has the highest dielectric constant. I can have it. I can have an acid, I can have an alkaline, I can have a simple salt. Any of those things are possible over here. But aqueous electrolytes are always a problematic because of a short circuiting and all those things will have a problem. So that's not really advisable. But the next good option is going for a non-aqueous kind of a system, which Professor Ramesh was talking about it. I can think about an organic materials, acetonitrile is the best option, people use it, but that's not really advisable. I can have an ionic liquids, I can have other kind of conducting systems can be possible over here, or I can have a solid state. This is the best option, people are working on this one, that's a solid state one, or I can have a redox electrolytes, which can, this falls under the pseudo capacitor, this falls under the bilayer capacitance over here. So now the most of the research happen in this part of domain of the electrolytes and using ionic liquids as part of the electrolytes over here. That's where the major part is happening. Okay, now when it comes to the separators is it's a very important system because I don't want to have the left and right to be short circuited. I want only the ions to move in and around from the left to right and the right to left. I don't want the electrons to move, so that I don't want to have a degradation of the system. Okay, so that means the separators becomes a very good, very important system. But generally what we use in the laboratory is I can use a cellulose, I can use paper, I can use Nafion films, I can use any of the polymeric materials which are conducting polymers, I can use it. These are to start in any laboratory, I can start with Wattman paper. Okay, that's the best separator I can start with, or a simple cotton cloth will be good enough to start with. Right. Now the next one is I need to worry about the current collectors. The current collectors means where I'm going to do the contact over here. Now that becomes very important because that can also bring about resistance. It can also bring up the degradations. There are a lot of things are available. Generally in the laboratory process we use nickel foam. That's the best one possible. I cannot use the nickel foam let's say in an aqueous medium or especially in the basic medium. It's not possible to do that. But in an acidic medium, this is very good. At a very low basic medium, this is possible. I can use a non-corrosive metals like gold, platinum, but they all suffer by a huge cost over here. Tungsten is a good choice, but there are very few reports available onto this one. This is 10 to corrode. And all we require is a less expensive like carbon fiber, carbon nanotubes, graphite foams, ITO plates, steel. These are all the general current collectors I can start using it. That means I can use these as the electrodes to start with to work on this particular one. Next, I need to worry about what are the characterization techniques. Generally, we have three characterization techniques: cyclic voltammetry, galvanostatic, electrochemical impedance. If you do these three things, obviously your whole capacitor or the battery characteristic will be fully being characterized over here. And what we have is a cyclic voltammetry. This is of a typical capacitor. I have a rectangular face. Now I could see the differences over here. They are all pseudo capacitor because they are all Nernst relation. So once if we start looking at these differences, That means you are no more in a capacitor, pure capacitor, I'm looking in a pseudo capacitor. So that's the first indication. Obviously, I need to do a lot of experiments like where scan rates and all those things have to be done. The next one is what is called the galvanostatic charge discharge. Sorry for it, I need to really rush it up. I have another 10 more slides or something like this. This is how the typical capacitor will look like. I have a charging, I have a discharge, I can have a different loads over here. Look at this at 5 milliamp, I have a long time, I have 15 milliamp, it's a very short time discharge. 25 milliamp, the time becomes very, very short, okay. So, this is the typical capacitance. Look at this discharge capacitance over here. I have a very slow discharge over here. So, that this is the battery part of it, and that's a typical capacitance part of it. So, I have a capacitance which is now here, and then I have a battery characteristic. So, this is the kind of charge discharge cycle you will be seeing in your pseudo capacitors. And the next I need to really worry about it, we talked about the resistances and distributed resistances. We generally look at electrochemical impedance. That's how a typical capacitor should look like, and that's the way you look at it. Okay. So these are the differences, the semicircles, the length of the semicircles, and all those things will now tell you about the electrochemical impedance. Okay, I'll just go through this. These are some of the materials which has been the two-dimensional material, and then we have a whole sort of a thing that's a human hair, and all those things have been reported over here. Okay, and these are some of the literature. The huge lot of reports are available. Let me just take where to start about it. Just give me 5 more minutes. I'll just finish it off. Okay, let's say. Just a random check, okay, random check on a Google Scholar on the supercapacitors. We have from 2007, there are 12,20,000 English publications, okay, English publications. I have 12,20,000 reports are available. The journals have been sorted about any impact factor is about 1, okay, so I have a huge literature is available. If I look at it graphene based, I do have about 74,000 publications are available. If I'm looking at the metal oxide based, I have 40,000 available. If I have MXNs means metal carbides, metal nitrides, and that kind of a materials, I have about 16,000 things are available. Now, I want to start doing research on supercapacitor or in capacitor research. Already I have 12 lakh of reports are available. How do I start? Where do I start? How do I bring about a new material or new knowledge to this? That's going to be a real challenge onto this particular one. Okay, I'll just come to this. These are all some of the things we have been working on. These are some of the things we have been working. I'll just go through this. We have a huge list of materials we have been working on in our laboratory. I'll just go through this. Okay. Now coming to this. I have about 12 lakh publications available. How do I start doing research on this? That's where the first part comes over here. That's a computation based research. That's where we need to start. Professor Ramesh was telling we need to introduce 2 things. This is one of the new material which has come in, what is called LGPS, lithium, germanium, phosphorus, sulfur. This is all about the battery. I'll come to that later. Which has a range of about 5 volts, okay, plus minus 5 volts, and then it has a temperature range of minus 30 to 45 degrees, which is nowhere near to the existing batteries. It's a huge one. Now, how do we go about it? You go about it by looking at, these are also solid state batteries, looking at these 3 starting points. There is something called a materials project, which is the open sources available. And then you have a next one is called an automatic flow. This is called an A flow. Next, I do have a open quantum materials database. All these 3 things, and with additional institutes, there is something called a material genomic initiative, which takes care of the existing materials to start building the system. Let me just start with this. If I take the materials project and go into the system, you have a materials about 178,627 materials is being databased over here, which is the one which is the gave a random things today morning. I just got it done, and I do have a materials, and roughly if I really look at it, if I count it, there are about 15 samples are available. I could get all those informations over here. I can randomly start doing it. This is from the material project. Next one is an automatic flow materials discovery. Look at the kind of the thermodynamic and the electronic structures has been done. You have close to about of 35,30,330 materials thermodynamic data is available in this for you to search with, to start with. And I just started with a flow with a simple example like zirconium. Okay, I just randomly gave it. Look at this. I have closed about 1,727 entries with zirconium is available, whose thermodynamic parameters, crystal structure, everything is known to start with. This is you have a lot of flows up place, and this is an open quantum materials where you can give, let's say I just gave an example of nickel, magnesium, sulfur. So it produces the phase diagrams of these three material, alternative phase diagram, and it says what are the stabilities. So I can start from some here, and then I can start with this kind of a material and go into the computation to do about it. Okay, this is how people do about it. They actually, this is one of that, this is called molecular dynamics. You can see the lithium, the white one, actually the lithium moving around. Okay, that's how it's been different. And these are all the phase stabilities I need to design about it. I'll just go to the general one. All I have to do is very simple. Generate a candidate materials by substituting dopant from the structure prediction algorithm. I just take it from the database, take something else. If I have a magnesium, change it with beryllium, change it with calcium, do something else, and then do the computation, and then do all those things over here. And these are all different things I don't have a time to do about it. That's what finally I do get it. Let's say if I want to really looking at the lithium batteries over here, the first one, obviously there is no decomposition, but this is a typical equilibrium is set over here. Okay, so this is not going to be useful for me because the equilibrium is set. Once the equilibrium is set, no energy is being produced over here. On the other hand, this is a very good system where this is a non-equilibrium, but there is an electron transfer. Okay, so this barrier which allows an electron transfer to happen. Once the electron transfer starts happening, obviously there could be a decomposition can happen over here. Look at this one. I do have a solid electrode interface over here which doesn't allow the electrons to move, but it allows the lithium ion to move over here. So that means I have a best option over here. So I need to choose this kind of a materials. What is this orange color? That's where my database and everything will let me know about it. These are all how to engineer the things and all this. All I have to do is we need to have a good computation. In order to bring about a new things, that should be the thing. The future is going to be the computational modeling. I take the database, I start doping it, do all the computation, go back into the experiment to continue to do the experiment. Okay. Thank you very much for this very brief. I know that probably they took a liberty with me because I'm a known person to this institute. They took a liberty with me to hurry it up on the lecture. Anyhow, I thank the organizers for inviting me over here for this lecture. And of course, I went through all those things. You are free to contact me at any time. You are free to come to my laboratory at any time you want to do it, either in the weekend or in the evening 4:30, 5 o'clock. Somebody will always be there. And my laboratory is open for everybody. Okay, it's open for everybody. It's a Government of India funded. So it's meant for the whole public. So you can always invite it to my laboratory to practice your either the short term or a long term or research. Thank you very much.
We are deeply grateful to you, sir, for your thought-provoking speech. And we appreciate your presence at our conference. Thank you, sir. Dear participants, now we have a tea break, and girls students are requested to move front door, and boys are requested to move at the back. So I request all the participants to be present after 10 minutes, okay, for the next session.
Participants, girl participants, please use the front door. Boys, please use the back door.
Anger. Hey, no, don't.
Hello.
Students are requested to settle down faster. Maintain silence. Hello. Hello. Participants, settle down faster. Participants are requested to settle down faster quickly.
Here.
Thank you. Am I audible? Am I audible clearly?
Yeah.
Yeah, okay. So please let me know when I have to start. Okay. Please let me know when I have to start, then I will start, okay?
Okay.
Okay.
Please, a conference with technical session focusing on exploring surface enhanced Raman scattering activity, applications of 2D materials and heterogeneous. It's our privilege to have Dr. Shankari Goswami, Assistant Professor of Physics at Vidyasagar College, University of Calcutta, as our chairperson for this session. Dr. Sanchari Goswami is an assistant professor in Department of Physics, Vidyasagar College, Kolkata, under University of Calcutta. She did her PhD, University of Calcutta, and then did her postdoc from SN Bose National Center for Basic Science. Her field of research is statistical and condensed matter of physics. Her research expertise
Okay,
lies in
thank you.
statistical and condensed matter physics with a strong. Yes, ma'am, you can take over the session, ma'am.
Yeah, okay, thank you. I would like to thank the organizing committee for giving me this opportunity to chair this session at such a wonderful conference. And I guess the Department of Physics and Chemistry both are organizing this. So let me first introduce Dr. S. Santosh Kumar. We will give the talk in this session. Dr. S. Santosh Kumar is a postdoctoral fellow at National Sun Yat-sen University, Taiwan. And his research is mainly based on nanomaterials, surface enhanced Raman scattering, energy materials, and catalysis. He did his PhD in chemistry from University of Madras. And after that, he did two postdocs. One is he still is pursuing one, and the first one is from University of Madras, and the next one is at National Sun Yat-sen University. Dr. Santosh Kumar's research is based on basically the synthesis and application of 2D nanomaterials, metal oxides, quantum dots, and polymer nanohybrids. His of colloidal nanoparticles and the development of nanomaterials for application in catalysis and several other ways. And he uses the techniques like XRD, TEM, Raman and FTIR spectroscopy. He already has published 20 research papers in reputed journals, and he has presented his research at more than 15 national and international conferences, which is also very good, I guess. In 10 reputed journals, he acted as reviewer. So we would like to hear his talk. Dr. A. Santosh Kumar.
Thank you for
Yeah, dear participant, you are requested to maintain silence.
Hello, ma'am. Can you hear me?
Hello? Yeah.
Hello. Thank you.
Yeah, I can hear you.
Can I go
Thanks.
present? Yeah, thank you.
Yeah, of course. Yeah.
Hello, sir. Hello.
Can
Sir, your voice is not audible, sir.
I didn't start, ma'am. My PPT is showing.
Yes, sir. You can start
Hello.
the proceed, sir.
Yes, your PPT is there.
Yeah. Thank you so much. Good afternoon, everyone. Hello. Can you hear me?
Yes, sir. Sir, can you make
Yeah,
the
yeah,
PPT to full screen?
Yes, wait a minute.
Okay, sir. You can proceed with this PPT, sir.
Wait a minute. Ma'am,
Sir,
now
you
it is
can
visible.
proceed, sir.
Okay.
Yes, sir. It is visible, sir.
Good afternoon, everyone. I'm very much happy to be present in this session. I would like to thank the ma'am who introduced me from the University of Calcutta and the organizers to invite me for this wonderful international conference on the topic nanoscience and computational modeling. My research topic is I'm going to present here exploring surface enhanced Raman scattering activity, its application to 2D materials and their heterojunctions for these SARS applications we are going to discuss here. I'm Dr. Santosh from National Sanyatsan University. Already they introduced. So I will go to the next slide. Now, 1 minute, ma'am. It's not moving. It's not.
Sir, you can just share your entire screen. I hope it will be moving then. Just share your entire screen.
It is not sharing, ma'am, actually. I'm sharing it. No. Entire screen, yeah. Okay. Now,
Yes, just go to some other slide. Go to some other slide just. Ah, yes, it's moving. Yes, right. Yeah.
yeah. Because of Raman's spectroscopy, we need to know about the spectroscopy first. Basically, what is spectroscopy? It is a study of absorption and emission of light and their radiation. When the light shine on the matter, it can reflect, transmit, absorb, or scattering. It is depends upon the wavelength of the radiation. Basically, optics is a study for the understanding about the light. Light is a electromagnetic wave. It has dual nature. One is wave nature, another one is particle nature. We are going to discuss about Raman scattering. Without ER and UV understanding, we cannot understand Raman spectroscopy clearly. When IR spectroscopy is a vibration spectroscopy, in this spectroscopy, when the IR source the light incident on the sample, it will reflect and transmission will happen. When the molecule get vibrated, then the transmission was recorded, and then the functional groups are identified using the data. From the UV visible spectroscopy, when the light source pass through the monochromatic filter onto the sample, it get absorbed, and then the data was processed. It is a electronic property of the material to give this kind of data while absorbing the light. But in the case of Raman spectroscopy, when the laser light excited on the material surface, the material undergoes the vibrational changes. It gives three kind of spectra based on the energy levels. This particular characteristic was discovered by our great Indian professor Sir C.V. Raman in 1928. He used sunlight to heavily filter with the filters and make this light into the shine onto the material surface, and it get scattered. He noticed that the energy of the incident and the scattered are very different. So for this contribution, he was awarded Nobel Prize in 1930. What he observed in that spectroscopic technique, there is three kind of spectra he observed. One is for Raman scattering, Another one is Rayleigh scattering. Raman scattering has two type of lines. One is Stokes lines and anti-Stokes lines. When the energy is higher than incident light is called Stokes line. When it is equal to the incident light energy, the emitting light energy is equal to this incident light is called the Rayleigh scattering. If it is lower than the incident light, it's called anti-Stokes. Well, Stokes lines are low energy but higher possibilities. Anti-Stokes are higher energy but low possibility. But compared with these two, Rayleigh scattering is more intense, but we never consider about the Rayleigh scattering. Only Stokes and anti-Stokes energy we can take for the account. So the energy difference in this spectral line, he noticed with the molecule get absorbed on the light. When shine the light, it get absorbed and then emit or scattered. So this energy difference makes molecule give some internal spectroscopic characteristics of the material with the vibrational and rotational characteristics. So it is a inelastic scattering technique. So what happens when the photon light get incident on the surface of the sample state, which contains the sample, it get absorbed, transmitted, scattered. All the things were happen here, but the scattered light can filter using the notch filter, and then it reflect on the mirror to go directed to the amplifier, which is monitored by the CCD, and then go to the monitor, then give the spectra. This information highly valuable for the functional groups of the materials. Some of the lasers, because Sir C. Raman used sunlight for this discovery, but after the development of optics technology, they invented the laser light. After this laser light, this particular Raman spectroscopy, not only Raman spectroscopy, many laser wherever the laser they are using for the studies, that fields are get attention. After the development of laser technology, Raman spectroscopy moved into the next level of its application. Different kind of laser wavelengths are they used for the analysis, and also the CCD detectors also they developed many things. The fine one is nowadays the pixel array of 1024 into 256 is commonly using for the Raman analysis. What is the main selection rules for the Raman scattering occurring? There are a few selection rules are available. One is vibration selection rule. When the transition can occur with the change in the vibrational quantum number must be plus or minus 1. It may be due to the Stokes line appearance or anti-Stokes appearance. The change in the polar velocity must be not equal to 0. If it is equal to 0, it won't give Raman signals or inactive in Raman scattering. Symmetry conservation. These modes that belongs to the totally symmetric representation in group theory, it always Raman active. When if it is non-symmetry mode, it may be inactive, not surely, because if the sample has center of inversion, it will it will play the important role in the Raman or IR active things. Mutual exclusion principle also telling the same thing, which is center of symmetry of molecules and vibration modes that are IR active are typically Raman inactive. It is vice versa. Rotational selection rules also there. For rotational Raman transition, it must be, the rotation must be 0 or plus or minus 2. These are quantum numbers of particular molecule which we use for the analysis. We can see the difference when the polarizability, if polarizability is here, it is not equal to 0 because 1. So it is not equal to 0, 1 plus 1 is 2. So plus or minus 2 is okay. But when you use minus 1, minus plus 1, it equals to 0. So Raman inactive. So these kind of selection rules are available for the Raman characteristic studies. So here we are here showing that Raman spectral regions of some of the functional groups which is used for the primary analysis of the peak presence for the functional groups. It has many regions like low frequency fingerprint region, double bond region, triple bond region, and higher frequency and overtone combination bonds. These each regions indicate a particular characteristic of the functional groups present in the molecule. We can see these, some of the spectra presented here. These were used for the, this data can be used to analyze the peak present wherever the peak exists. So the functional group can confirm with these regions and these frequency matching. So this is highly informative point that we must know the regions of the functional groups for the Raman spectroscopy analysis. So the common information, what are the informations we get from the Raman? Here we can see this, the composition of material. When we have a multi-component material, we can analyze through Raman and then get what are the composition present in it. We can also test the strain of the material and the crystal symmetry and the orientation of the crystals we can see. We can also estimate the quality of the crystal which is used for the analysis. So some of the organic functional groups were present here, the molecules and its regions also present here. You can see here. So what can Raman do for us? Raman can use to analyze various type of materials in the broader application areas like medical field, pharmaceutical. They are used to quantity and qualifying the drug molecules who discover in the pharmaceutical industry, and in the food they are used for the qualification of the food, the food package and the contaminants and everything. In the semiconductor manufacturing, they used for the quality of the chips they made with the defects and the phase transformations we can see using these Raman. So they are science, geology and mineralogy, they used to analyze what are the compounds present in the Mars and everything. So like many fields they use. But however, the Raman has certain limitations, like laser source may have fluctuations, need an internal stand for the standardization of quantitative works, weak signals its efficiency is very low, and sampling, we need to focus more on the preparation of sampling, and the most and the fluorescent interference of the uh, analysis. So to overcome this, Raman spectroscopy evaluated so long way after the discovery of metal nanoparticles. They discovered the SERS is the updated Raman version, maybe we can call is 1974. Until now, it changes in many ways due to the many reasons, like introducing some concepts and some of the new things into combined with the Raman spectroscopy. It travels like this. So we are going to talk about Raman's enhancement. The Raman's enhancement, generally they call surface enhanced Raman's scattering. It is a phenomena that when laser beam laser beam shine on the sample, it shows some Raman peak. But the difference when silver or gold or copper metals presents, we can mountain the sample on the surface of these coinage metals. Then we shine the laser source. It will give some Raman spectra. We will compare both Raman spectra when silver and gold, like metal based analysis shows higher SERS intensity compared with the normal one. So these two scientists, Martin Fleischmann and Richard Van Doene, have a big confused why it happens. Then they proposed the mechanism what happens in 1977. Electromagnetic enhancement theory they were proposed. Because of the silver and gold nanoparticle, it has SPR property. The surface oscillating electrons contributed to the peak enhancement and make the peaks are very high in the low, even have a low concentration of the sample. So in the same time, the Albertchet and Crichton, the both chemists in the same year, they have reported it is due to the charge transfer between the analyte molecule and the laser light. So two kind of theory in the same year they proposed for this SERS enhancement. However, what are the Raman spectroscopy problems they faced? Then how SERS give the solution for that is presented here. Already I told that Raman have a many drawback like weak scattering, fluorescent interference, long time acquisition time, poor detection, other actually the low concentration we cannot achieve, and background noise is so high, so sensitivity also very low. When using this SERS based technique, they can enhance this signal because of the electromagnetic charge transfer theory, and also metal nanoparticle can quench the fluorescence of the analyzing samples, and it can be used to detect very quick detection, and also we can reach up to single molecular level detection, and the selectivity also is very good, and then sensitivity is too high. So because of these properties and nature, SERS get more attention among the researchers, spectroscopy researchers. Then they have proposed many criteria for these SARS activities. They proposed mainly preparing silver or gold coinage metal nanoparticles in the different way with a different morphology, different shape, different size and different SPR property. Like the range, the wavelength range of SPR also they alter, and then they have checked how these properties can affect the CRS intensity and the Raman enhancement. And they confirmed with the excitation wavelength as significant impact on the spectral changes. Here we can see the 532 nanometer shows very less intense, but 785 nanometer shows high intense SARS spectrum. Here
Excuse
we
me,
can
sir.
also see, yeah.
Excuse me, sir. You have 5 more minutes. Okay.
Okay. Okay.
Oh,
We
okay.
can see here, yeah, we can see here different kind of nanostars, nanorods, nanospheres like shapes they have designed, and then they have checked this Raman scattering activity when the more edges can find in the star shaped nanoparticle shows higher enhancement. Like hotspots, the very nearby nanoparticle give more SERS enhancement than the single nanoparticle. And also the nature of the material, gas, liquid, soil, solid, or the color of the material also influencing the SERS enhancement. So they have calculated using this formula for the how much of the SERS get enhanced or decreased. So will the even size of nanoparticle presents the RSD value, the relative deviation is very high. If it is very high, then the SERS substrate is not worth to use. But if it is very RSD value is very less than highly valuable SERS active material that we can produce. Here we have focused on 2D materials and their heterogeneity for this kind of SERS enhancement. 2D material like graphene, boron nitride, TMD materials, transition metal dichalcogenates, and the other 2D materials combined with the silver, gold, copper, palladium, rhenium, like metal nanoparticles with different shapes. They can use to analyze the material, and they can observe the SERS monitoring, and compare with the normal and the other type of SERS substrate. This particular substrate, these 2D combined heterogenations are show both electromagnetic and charge transfer effectively, and the other opportunities like pi interactions of the analyte into the SERS substrate add good interactions, give more sensitive nature. So some of the researcher they use for these SERS technique, these 2D material heterojunctions for analysis small chemical molecules with low concentrations level. Here, this work graphene oxide silver nanocomposite used for the PAH reductions, polyaromatic carcinogenic materials. Likewise, this work discussed about the graphene and the boron nitride based SERS substrate for the low level reduction of dyes into the water. Here the MOS2 silver based different morphology of the MOS2 and the silver nanoparticle were used to detect the dyes in the food contaminant, and they were reported. Likewise, many 2D materials were used. but the less study focused on the gravity carbonated and TMD materials. We are just used these kind of materials for these particular enhancement applications. Yeah, we have used silver and gravity carbonated as a CRS substrate to detect toluidine blue dye up to the 10 to the power of minus 9 molar concentration and has good reproducibility and everything. This particular work is highly important because of toluidine blue is a important biological molecule. It's also a kind of dye which is highly useful for the medical sectors. They use this dye for the staining the organs for the many analysis. And also we have developed gravity carbonate contain beta cyclotextine and silver pesticides like material. So this you usually used in for the agricultural land. So we have detected this notably up to the 10 to the power of minus 9 molar. We have published this paper in Dalton transaction, and also we used MOS2 alone without any plasmonic materials, and we just make effects on the surface of MOS2 by chemically. We are the first person we did this, and then we published this paper in Journal of Physical Chemistry in American Chemical Society. It is the best journal in the field of physical chemistry. Because of the chemical treatment on the surface of MOS2, it shows some defects, and then these defects helps to the dye molecule interacting well on the surface, and the charge transfer of the more convenient possibility of DLLME. It is a dispersive liquid micro extraction technique. Then we achieved very low level detection without any other plasmonic materials or another like here chemical etching anything. So this particular technique we applied for the red chili contaminants to detect these dyes present in the red chili. We have reported in this journal, one of the best sensor journal in the elsewhere. So how the small molecule are very caution to the or very important to the human. The same thing like heavy metal ions also have a big environmental and biological problem. There are for human it gives more problem for their health risk. When these heavy metals present in the drinking water, food, and everything. Usually, many techniques are available to detect these metal ions, but the sensitivity is questionable. When using Raman scattering, it is we can achieve a good sensitivity and selectivity. In the regular Raman spectroscopy, they use silver gold nanoparticles for this, but without 2D materials they are using, it is highly expensive if we use only gold, silver like metals. So some of the research group they have used graphene and reduced graphene like 2D materials for the sensing of these metal ions. Mostly they use to sense the lead ions in the environmental without the interference, but the preparation method and the concept they introduce or it seems to be clumsy, and we developed a very simple method, and also it is a liquid. You can monitor this by liquid itself. We achieved very low level detection up to 0.02 ppm, and the another work is 0.09 ppm. So combines graphic carbonate with graphene oxide, it shows a good sensitivity compared with only graphic carbonated silver based. We used methylene blue as a intermediate to when we use this methylene blue to sense by Raman scattering. Then if you add mercury on this, it will eject from the surface of this new concept we introduced. Then this paper got accepted in the spectrochemical acta, and then the updated work which we introduced graphene oxide and GCN together. We published in Applied Surface Science. The important thing is the electronic declocations play important role in the sensitivity enhancement. So this particular work get good recognition. Still, it is these two papers are very highly cited papers of mine. Like
Sir, kindly conclude because we are actually running out of time. Yeah.
Yes, ma'am. Yeah, given very less time already. Okay. The another kind of application that monitoring of catalytic reaction by SCRS, usually UV visible spectroscopy were used for the monitoring the in situ catalytic reactions, but many of them nowadays working with the Raman to monitor this type of catalytic reactions. Some of the 2D materials with the silver nanoparticles they have reported to monitor the dye degradations and the other catalytic reactions. Here they used graphic carbonated and gold as a Raman's SCRS substrate to monitor this degradation. And here, graphene oxide coated nanowires were used to monitor the nitro to amine coupling reaction, nitro to amine conversion by coupling of NN bond. In this particular study, they didn't use any reducing agents or oxidizing agent for this. They just used plasmon electrons for the conversion to monitor this CRS reaction. By in the same way, the graphene oxide converted into reduced graphene oxide, they used methylene blue degradation monitoring. In the same way, graphene oxide and silver with iron oxide used for the methylene blue degradation monitoring. Yeah, in the other way, the polymer containing silver and graphic carbonated material were used to monitor the degradation of catalytic degradation of methylene blue, and then thiosobenzazole antifungal agent also they have used to monitor the catalytic degradation. In this case, we used graphic carbonate silver nanoparticle as a CRS substrate to reduce the methylene blue, and we can monitor through the Raman scattering technique with in the liquid form, and also it has many advantages like simple preparation method and the cost effective, and also higher rate constant. We can be able to monitor in very low level of methylene blue present into the water. We can degrade it and monitor it. So it is highly important thing. So finally, the SCRS of applications of SCRS also extend into the many research areas like food safety monitoring, forensic science. Nowadays, machine learning also they used to combine SCRS and machine learning for the high and accurate sensing of Raman scattering. Raman scattering of the material, and many by concluding this, many 2D materials are present. Silver, gold, like metal nanoparticles also present, but they used very less number of materials to combine both and used for these particular applications. The lack of research noticed for the borofin, MOF materials, and these MX in materials. So researchers who have interest on this field, they can choose these materials for the particular the discussed particular applications. Finally, I would like to thank National Sanyatsan University for providing me the facilities over here, and the NSTC for the fund. And also, I need to thank my professor, Professor M. Palanichami, the Emeritus Professor, Anna University, and my research guide, Professor E. Murugan, Department of Physical Chemistry, University of Madras. And also, I would like thank my postdoctoral mentor, Professor T.W. Singh. He is the person who motivated me to do this remarkable research. And I would like to thank Dr. A. Christie and Dr. T. Sivaranjani. They are constantly supporting me to bring me to this conference. And I would like to thank the management, Sri Manakula Vinayagar Educational Trust, and the organizing committee and the other staffs who work for the ICNCM 2025. Thank you. This is my research group. He is my professor. If you have any question, kindly let me ask. Thank you.
Thank you, sir, for your wonderful presentation. Yeah, is there any question? Sir, I just wanted to know one thing. I mean,
yes, ma'am.
This is a experimental work. But
yes,
is there any kind of model you have thought of, like to explain the behavior or something?
Yes,
is there any kind of physical model?
Yes, ma'am. Yes, ma'am. Just we are starting to know the interaction of light with the metal surface and the analyte molecules using FDTT method, the finite domain time domain methods. Yeah,
Okay.
we recently started with that application. So it is on process now.
Okay, okay. So let us thank the speaker once again.
Yeah. Thank you, ma'am. Yeah, the FTDT based on work we are just submitted in the Angular. We are waiting for good news very soon. Yeah.
Yeah. Okay. Okay. Thank you.
Thank you so much. Thank you so much, ma'am.
And I would like to thank once again to the organizing committee and specifically Christy Ferdinand sir for giving me the opportunity to be a part of this. It's a wonderful session. Thank you.
Thank you, sir.
Thank
We
you,
are
ma'am.
deeply
Thank you.
grateful to Dr. S. Santosh Kumar for his thought-provoking speech, which provided valuable insights into the latest development in this field. Thank you for a valuable contribution at our conference, sir.
Thank you so much, ma'am. Thank you. Thank you for inviting me.
Thank you, sir.
Thank you, ma'am. Thank you.
Participants A very good afternoon to everyone. As we came to the last technical session, okay. We are pleased to resume our conference with technical session 8 on composite material fabrications and properties analysis. We are honored to have our chairperson, Dr. S. Xavier, Controller of Examination, Head, Department of Physics, St. Joseph College of Arts and Science, Cuddalore. His area of specialization is on molecular spectroscopy and computational physics. He has nearly 32 publications with 594 citations. Under his guidance, 4 PhD scholars pursuing their research work. Now I request Dr. S. Xavier sir to read out the guest profile of Dr. S. Periandi sir. Before that, I would request Mr. Udaya Kumar sir to honor Dr. S. Xavier sir.
Now I request Father to honor our Chief Guest, Dr. Periandi.
Thank you, sir.
Dear and respected the people from management, respected HOD of the Department of Physics, faculties from the Department of Physics and other departments, research scholars, faculties from other institutes, and dear students. Today I have a privilege to introduce my own teacher, my own guide. Usually we may not get a chance to introduce his own teacher or his own guide. Through the help of our friends, I got this privilege to introduce my own guide in this August gathering. A legacy in academia and research. I am going to throw a light on a legacy in academia and research. Dr. S. Periandi is a distinguished scholar. When I say few words about him, it's not flattery. It's not a glorious words that I coined, but something that is very reality. I am giving you all. An inspiring educator His own students are seated in this beautiful auditorium. They witness all those words that I am going to tell. An inspiring educator and a dedicated mentor known for his unwavering commitment to students. He goes the extra mile to nurture their talents and unlock their own potential. As a teacher who remains deeply engaged with his students, he fosters an environment of learning and innovation. Wherever he is present, you can see a great innovation, a great learning atmosphere. Beyond academia, Dr. S. Periyandi is a well-renowned researcher, a passionate social activist, and a celebrated columnist. His contribution to the field of spectroscopy, particularly quantum mechanical methods and spectroscopical techniques, are positioned him as a leading expert in this region. If you want to search for an expert on spectroscopy, just approach Dr. S. Periyandi. Is none equal to any of the experts moving around in this region is par excellence. Academic contributions and achievements. You may not be surprised when I see the quantities of his achievements. His publication is 204. Can we give him a big clap? His research papers, all the papers. You may be surprised to see and enlisted all his papers only in the Elsevier journals. That's the beauty of beauty that he holds. And he has guided 28 PhD scholars. He has got a very powerful citations, I would say. 3,554. Let us give him again a clap. His H index is 34. His I-10 index is 83. When you read these quantities of the research, one cannot find in this region such a beautiful and powerful quantity of the research achievements. Dr. S. Periyandi is not just an academician, he is a legacy in motion. I put this word purposefully, a legacy in motion. Leaving an indelible mark on education, research and society. At present, he is an associate professor at Kaji Mamunivar Center for Postgraduate Studies, teaching physics and guiding the research scholars. With this short note, I welcome him to take up the session. Welcome, dear sir.
Thank you. Thank you, sir. Thank you, sir.
Good afternoon. Respected the management, the head of the Department of Physics and Chemistry, distinguished guests from other institution, faculties of this institution, dear research scholars and students. I'm very happy to stand before you at this occasion to present a few research output of our team. The person who has done that work is sitting here in the first row. The work is about the composite material. What is a composite material? Actually, any material which is made up of a combination of more than 2 or 3 different types of material. The composite material will have metals, will have ceramic materials, will have polymers also put together. What is the aim? So that is the definition for the composite material. And based on, usually all composite material will have one base material, which will constitute the 95, 97, 98% of the material, the composite material which were produced later. The other 2 or 3% of the material will be of different kind. What is the purpose? Is to increase or enhance the properties of the base material. So now we are going to have 2 terminology. One is base material, the other one is added material, and that added material we are going to call it as reinforcement material. So based on the base material and reinforcement material, there are now 4 types of composite material. One is called fiber reinforced polymer, where both are fibers or polymers. Both the base material and reinforced material are polymers. And this is ceramic matrix composites, where both are ceramics material. Base material as well as the reinforced material are ceramic materials. This is called the metal matrix composite. In this, the metal is the base material. The reinforced material may be other things. The hybrid composite, slightly the base material is also a composite material, and with which we add some more ceramic and polymer material to make it much more stronger. So this is the diagram or flow chart which tells us how these composite materials are generally prepared. In our study, this is the base material, which is called as aluminum 6061. This material is a very special material prepared by a company, a research and development company, Alcoa in USA. The purpose why they invented that material, why they made that metal, is to purposefully use it in aerospace industry. In all the machineries used in aerotechnology, as well as in the automobile industry, this material is being used, aluminum 6061. It is a very special and novel material. It consists 97% of aluminum only. You know that aluminum is very soft metal. But after making this, some addition into this material, making it as a composite material, it has been found it is enormously strong when compared to the base material aluminum. So that is the advantage of making a composite material. What is our work is to increase further to increase the qualities, the desired qualities of aluminum 6061 by adding some more reinforcement material. So this aluminum 6061, being it almost aluminum, its melting point is 660 centigrade. So now we heat it to 750 degrees centigrade. We make it completely in molten state. We keep it in the furnace. Now this is the reinforced material or the material which is going to be added here. In this case, what are the material we are going to add is boron carbide, silicon carbide, graphene. We have three types of material to be added here. In three different fashions we are going to add it here. So these melting points are very high when compared to the 750 degree. Actually the melting points of silicon carbide and boron carbide is above 1500. So they won't melt. The particles as such can be combined with this molten aluminum material. So actually we take this material in nano size. Usually so far they have not taken any, making the composite material, they have not taken nano materials. First time we have taken in nano sizes the particles to be added here. So they will also be preheated to around 350 degrees centigrade, and they will be kept ready. When the molten form of aluminum is here, they will be mixed and stirred. There are two types of stirring is happening there. One is mechanical stirring. The other one is also being used, that is called ultrasonic stirring. And the ultrasonic stirring has one more advantage also. It produces voids. It produces vacancies in between so that the particles can go and accommodate. So that is the advantage. So in this way, the samples are prepared and the samples are subjected to, and the samples are subjected to two different studies or analysis. This analysis is merely to identify whether the sample is in accordance with our the making procedure. And this is the studies which tell us whether the material prepared is going to be of good quality, of desired quality or not. So whatever I said earlier on the chart, this is written here, how we prepare the samples. This is the content of the base material, aluminum 606. This we ourselves have analyzed using the using the WDXRF method, that is called wavelength dispersive X-ray fluorescent analysis. What we do that is, on the material aluminum 6061, we pass X-rays so that we make them to fluorescent. All the elements present in the aluminum 6061 are stimulated to fluorescent radiation. From the amount of fluorescence and type of fluorescent radiation we receive, we identify the element present inside the aluminum base material, and we also find out what is the ratio in which they are present. So this is the result says that the aluminum is 97.6%. The other things are there. Some of them are metals and some of them are ceramic materials. See here one result is there. These are the boron carbide is added in 300 nanometer size initially, and silicon carbide is of 50 nanometer. But before they combine with the base material, they are subjected to the ball milling method so that they are further crushed into smaller sizes. And this is the density. The density, here is 2.71, 2.52, 3. Here the base density is this. The silicon carbide density is more than the base density. After making the sample, we have found that the density of the material, composite material that we have prepared has lesser density than the base material density. The density was decreased because of the what is called the holes, because of the holes present in the made sample. Here the thermal property, initial starting thermal property of these materials separately. This is the thermal coefficient. These are all we are going to study later for the prepared composite material. This is the melting point. As I told you, the aluminum 6061 is around 620, pure aluminum is 660, and this is the melting point individually for boron carbide and silicon carbide. Specific capacity, okay. So first we are going to see this combination. We are going to have three different samples with the contention is the aluminum 6061, this is the base material. Silicon carbide is added, very small amount of silicon carbide, 0.58%, and boron carbide is also 0.5%. In the remaining two samples also, this boron carbide concentration kept constant, whereas the silicon carbide is enhanced to 1 weight percentage and 1.5 weight percentage. This is the FECM field emission scanning electron microscope view of the samples present, and this sample is 0.5% of the boron carbide and 0.5% of silicon carbide. The first sample, first composite sample present. This shows these are the particles, what for the present of the particle, this would have been much smoother. Now the particles are present, that shows the distribution of the particle is almost uniform. And here one particular interesting factor is that this is 200 nanometer, the length of the green scale, that is for 200 nanometer. When compared to this length, if you see the sizes of the particle, that shows it is lesser than 200 nanometer. Though we have added boron carbide with the 300 nanometer size, this shows almost all the particles are crushed to a size lesser than the 200 nanometer. This is for the next sample, and this is for the third sample prepared. And here, you may not be seeing it here clearly. And this is, and this is for the base material, and this is for the one of the sample prepared, one of the composite material that we have prepared. And what are the elements we have added? It is a confirmation whether all the elements are present here. The small peaks here tell us that all the added elements are present within this sample. It is a proof that our sample is rightly prepared. And this is called, what is this spectrum is called? Energy dispersive spectrum. How this energy dispersive spectrum is working? Again, on the samples, X-ray should be irradiated. And the sample in turn, these elements will absorb these X-rays. In turn, they will re-emit their own characteristics X-rays. Characteristics X-rays means every atom will have its own natural X-ray spectrum. So those X-rays will be emitted. We detect those X-rays. From that, what are the elements present inside the sample? We measure and calculate. We draw the spectrum. So this is the X-ray diffraction spectrum. And this is the base aluminum 6061 X-ray diffraction spectrum, which has only 4 peaks here, all for aluminum only. All for this X-ray diffraction is for aluminum 6061, where some of the elements are also present, but it is so minute, we get the peaks only due to the aluminum. This aluminum has a crystalline structure of phase FCC, phase-centered cubic center. Then if you write from the first sample, for all the samples here, you can see the peaks are almost the same. But when we see how these peaks are produced here, This is boron silicon carbide. We separately add boron carbide, we separately add silicon carbide, but inside in the boundary, some of the particles merge together and they produce a different crystalline structure. That is what these items are shown. This is boron carbide, this is boron, this is aluminum carbide. There is no substance we have added as aluminum carbide, but the peaks present shows that such combinations are also available. That shows there is a multiple crystallinity is produced and the boundaries of the particles added. So actually the silicon carbide crystalline structure is hexagonal and that of boron carbide is rhombohedral. Now we have come to the properties of the material that we have prepared. This is more important. Now we have produced a composite material. Now it is very important. Actually, these things should be immediately patented. Otherwise, somebody will use it. Very important material. Industrially, and that too for making rockets and aeroplanes, these materials are very important materials, highly commercially very important. So what is the first property we have measured is the hardness of the material. The hardness, there are two international standard methods. One is called Vickers method, other one is called Brunel method. And the green bar diagrams represent the Brunel result and the other one is the Vickers result. This is for the base material. This is the hardness of the pure aluminum 6061. Now you see, after adding the reinforcement material, for the first sample we are seeing here now. This is sample 1, this is sample 2 and this is sample 3. You see, for sample 2 almost the double the amount of hardness is produced here. It is lightweight material. All the composite materials are lightweight materials, but it is a very hot material. Very hot material. This material, say aluminum 6061, was recommended by Dr. Abdul Kalam when he was the President of India for an industry which makes artificial limbs. நம்ம இந்த செயற்கை கால்கள்லாம் சொல்கிறோம் இல்லையா, அந்த காலத்தில் ரொம்ப வெயிட்டாக இருக்கும். ஒரு சின்ன பையன் ஒரு செயற்கை கால் போட்டு நடந்து போய்கிட்டு இருக்கான், அவனால் நடக்க முடியல, அவ்வளோ வெயிட்டாக இருக்காது. ஜனாதிபதி அவரை பார்த்துட்டு ஏன் இவ்வளோ வெயிட்டில் ஒரு ஆர்டிஃபிஷியல் லிம்ப் செய்கிறீங்கன்னு சொல்லிட்டு வேறு வழி இல்லை அப்படின்னு சொல்லும்போது, அப்புறம் அவர் ராக்கெட்டுக்கு யூஸ் பண்ண அந்த மெட்டீரியலை கொடுத்து அதில் மோர் தென் ஹாஃப் வெயிட் குறைச்சி ஒரு ஆர்டிஃபிஷியல் லிம்ப் அப்புறம் செஞ்சான். இப்போ எல்லாருமே இந்த மெட்டீரியல் யூஸ் பண்ணுறோம், த்ரூஅவுட் வேர்ல்டு இதை யூஸ் பண்ணுறோம். ரொம்ப லைட் வெயிட்டாக இருக்கும், பட் வெரி ஸ்ட்ராங் மெட்டீரியலாக இருக்கும். தட் இஸ் தி அட்வான்டேஜ் ஆஃப் மேக்கிங் தி காம்போசிட் மெட்டீரியல். How they measure by making deformation, indentation, scratching and wearing. You make some deformation with the material. From that you can understand the hardness of the material. That is the technique. And this is the one-dimensional elastic property of the material that we have prepared. The Young's modulus, we can say. We stretch the material in one direction, in X direction. How much stretching can be produced for a given amount of stress or the pressure or the force? What is tensile yield? What is tensile strength? Specific tensile strength is the maximum force required to deform to the deforming point of the material. See, within the elastic limit, we say the stress is proportional to strain. That elastic point, after elastic point, the deformation will be produced. So, what is the maximum force up to elastic limit? That is called the specific tensile strength. So, the specific tensile strength, this bar, this yellow bar, So, with compared to the base material, the specific tensile strength has been enormously increased. This is around 33 and this is around 50. So, almost double the value it has been increased. And what is this UTS, ultimate tensile strength? This is the force required to completely break the material. Ultimate tensile strength, one-dimensionally, how much maximum force you have to give to break. So that also, you see, it has been tremendously increased by the the added material. What is the added material? Is silicon carbide and boron carbide. A few percentage, one is 1.5 percentage, the other one is 0.5 percentage. So only that percentage, tremendously, almost double the times it has increased the properties of the material. And what is elongation? What is the maximum stretch that can be produced? That is called elongation. What is impact energy? What is how much energy that material can absorb without deformation? So that is called impact. I'm sorry. The impact energy, this is impact energy. As the percentage of the reinforced material increases, it needs more and more impact energy to get it deformed. What is this is the elongation produced. The more the reinforcement material you add, the lesser the elongation you can produce. Means the higher the concentration of silicon carbide, the material is much more and more become stronger and harder. This is flexural and compressive strength of the materials that we have prepared. What is flexural is two-dimensional elastic property, that is bending. If you take in the form of a slab and you bend, and you know that the two-dimensional deformation will be produced. What is the maximum force, maximum pressure that is required up to the breaking point, up to the deformation starting point? So that is flexural and three-dimensional strength. What is the maximum force it will withstand before the three-dimensionally deformation? So here are the same pattern, exactly almost double the amount of elastic constants. The property we see that has been enhanced here. Okay. So what we have seen is so far, what will happen? Load to these materials, pressure to this material. Now, you see here, this is the word pressure. And the property acquired or the property responded by the material to the pressure. And that is one of the important mechanical property. There is another important mechanical property. What happens when they move? When they are, suppose if it is a rocket, it goes in a very high speed, what will happen to this material? So the friction, particularly, that is the property due to the motion of the material. And another property, very important property, is the temperature. What will happen if it is heated? These are all very important things as far as this aerospace technology, the engineering is concerned. So what we have seen so far is the properties due to the pressure applied on the material. And the other two properties combining, we call it as tribological properties. Very important word in mechanical engineering. Normally, this type of words, physics people, this type of works, this type of research, physics people won't do. Because it needs, we need to visit a lot of laboratories across the Tamil Nadu or Andhra, even Bangalore. And that is the difficulty in carrying out this work, because any one single laboratory cannot provide all these instruments. So now we will see what happens to this wearing rate. Wearing is something happens on the surface of the material. Understand, on the surface of the material you apply load or pressure, you will understand how much weathering it produces. So in the base material, the wearing is increases with the increase in the load. More the load pressure you apply, there will be more wearing of the material. In the base, aluminum, it is one of the finest material. But in the material we have prepared, no, it is not only very less, the wearing rate is not only very less, it also shows slight decrease in wearing with respect to the application of the load. நீங்கள் எவ்வளோ ப்ரெஷர் கொடுக்குறீங்களோ அவ்வளோ வியரிங் வந்து குறைவாக இருக்கு. சம்திங் வெரி சர்ப்ரைசிங் ரிசல்ட். And it happens here, it is coefficient of friction. The friction also on the surface, it is similar to wearing only. The friction also for a base material, it increases with the increase in the load. But friction decreases in the case of the composite material that we have prepared. It's one of the finest discovery. Understand, any material with respect to the load, increase in load, should give more friction only. But here it is observed in the other way. So this is the surface. Actually, this is the base material for a load of 10 Newton and 40 Newton. The surface FECM photo image. And this is one of the material we prepared. One of the sample we prepared. This is for 10 Newton load, and this is for 40 Newton load. This shows that when compared to this base material image, and this surface is more polished when compared to the base material. This is thermal property. How much the material expands for a given amount of heat for a unit sample, unit volume of sample. Here you see, this is the base material. The expansion is more in the material. If you give some amount of heat, the expansion is more in the base material, that is the original material. The expansion is very less for the material that we have prepared. The composite material that we have prepared shows lesser expansion for the same amount of heat. Whatever may be the heating produced, our material will expand very less only. If it expand more, there will be breakages, and there will be the engine may be spoiled, and ultimately the rocket or the automobile will be ruined. And this is thermal conductivity. Actually, aluminum is a metal, it is a good conductor. Now we are adding some silicon carbide, is a ceramic material, boron carbide, it is also ceramic, but it is insulated basically. Now you see, but silicon carbide, it will be mostly a semiconducting material. You see here, for all the temperatures, you take one row at least here, so let us take two here. Now this for base material conductivity is around 200. For sample it is 178. For the sample which exhibit the exemplary characteristics is 175. This is also 18. Means even though the silicon carbide and boron carbide are nearly insulated, but the final product is a good conductor, as good as the aluminum, as good as the base material aluminum, because we add in nano sizes. All these particles are nano sizes. We almost add only to a small fraction, 1.5 and 0.5. So the conductivity is retained here. It is a good conductor. It is it has a very less friction. It has a very less wearing rate, but its hardness is almost double. The mechanical properties are improved. That shows the product that we have now is a fantastic material. This is to measure the corrosion. This graph is between current and voltage. How we measure corrosion is, we put this composite material into a saline solution. We keep two electrodes connecting to positive and negative terminals. We pass currents, we apply voltages and measure currents between the plates. Now as the corrosion increases, a kind of layer will be formed on the material, and that will prevent that corrosion, that formation of the layer will prevent the current flow. That is expected from the current and the voltage. We can calculate the corrosion rate. The result is in the other slide. You see here. You see, I was talking about density, This is the base material density. You see the density of the sample present is less than the value. though the density of originally the boron carbide and silicon carbide is far greater than the aluminum density, now after they make, you see, this is the experimental density. The density is found to be lesser for the composite material that we have prepared. And the corrosion rate you see here. Originally for base material, 349 mil per year, and you see here it is 129, 99, 190. How much the corrosion rate is decreased? It is very less corrosive now. Understand? So the material that we have prepared is one of the wonderful material. So that is about that combination silicon carbide and boron carbide. Now we have another set of 3 samples with graphene and boron carbide. We have now removed silicon carbide. We added graphene with that. So now we will see, we will just rush through the results. எவ்வளோ நிமிஷம் நான் முடிச்சிருக்கேன்? உனக்குள்ளே பேசக்கூடாது, என்கிட்ட பேசணுட்டா? Okay. Now you see, we have only boron carbide and graphene. The graphene content is kept remain constant. The boron carbide concentration is increased from 0.6 weight percentage, 1.2, 1.8. And you see here, probably, no, in those first slide, the previous set of samples, the peaks are very large in number in the previous slide. Now drastically all the peaks are reduced only because of the aluminum and boron carbide. And there is no silicon carbide, there is no combination of aluminum, silicon, aluminum, boron, etc. So it's a very simple crystalline structure. And here the bar diagram for hardness remained almost the same, but you can see, as I told you here, it is relatively less. The maximum value is around 50 only. Previously it was around 70. Previously for silicon, with silicon carbide, the hardness was around 70 maximum value, and now the maximum value is around only 50. That shows graphene has helped. This is the base material. Boron and graphene both and silicon also has helped for the increasing the hardness, but the relative increase due to the graphene is less. That is the conclusion. And similarly here, for all the observation for the one-dimensional elastic property, two-dimensional, etc., all the values are relatively less when compared to the previous observation with the silicon carbide. And the flexural and compressive strength, this is the two-dimensional, three-dimensional, but the value, the two-dimensional elastic property has been boosted by you see the comment here, relatively increased. In the previous two slides, we have said it is relatively less. Now we say it is relatively more. That shows the graphene has helped the two-dimensional and three-dimensional property. And here, the coefficient of friction is still lesser. The graphene has helped to reduce the friction and the wear rate. And thermal expansion is also still less. It is still lesser than the previous value, means the amount of expansion is still less here. The graphene has improved the expandability, it has reduced the expandability of the material. And this is thermal conductivity. When compared to the previous value, it is much lesser. The thermal conductivity is slightly reduced. There it was 170, 180. Now it is reduced to 160. And the experimental density, you see, density is slightly increased here when compared to the previous value. And similarly, the corrosion rate is also slightly increased here. The corrosion rate, of course, when compared to the base material, it is drastically less, no doubt. But when compared to the silicon carbide material, this graphene material is slightly more. And this is the sample. Now we removed the graphene also. We retain only the boron carbide. Let's see what happens. So the peaks here is same as that with the graphene. Graphene was not present, it was not a crystalline material, so it didn't have any peaks in the spectrum, X-ray spectrum. Now it is similar to the previous one. Here it is still lesser, even with compared to graphene. With the boron alone, the hardness is lesser. It is 35 to only 45, 46, something like that. But it is gradual increases, Previously, the second sample used to have maximum value. Now it is not like that. With the addition of boron, we can now conclude still boron concentration can be increased. But the relative increase is lesser when compared to the previous two samples. The same observation for one-dimensional, two-dimensional, and also for this coefficient of friction, wear rate, and you see the thermal expansion, how closely the samples are very close to the base material. That means the boron carbide does not help much for the thermal properties of the material. And this is conductivity. The conductivity value is lesser here. Boron carbide is an insulator, and that is why drastically the values are very less when compared to the previous two samples. The corrosion rate. The corrosion rate is around, now here it is 270, 132, 140. This value is more when compared to the first set, maybe equal with the graphene experiment. Yeah, we have come to the end of the session. Actually, no, this work we have presented within 30-40 minutes, but it was the 4 years work, Actually, he prepared the sample in Coimbatore somewhere, and he got it characterized in Bangalore, Madras, IIT, so many places he traveled. He himself, the scholar, please stand up. He is Dr. is Venkatachalapati. He submitted his thesis. This is the work. He, being an assistant professor in government, he could afford this research. For this samples and measurements, he has spent nearly 5 lakhs rupees, which a regular scholar cannot afford. So, there is one advantage of being an earning member. So, this kind of research, actually any research on materials, the application side of the materials, the research costs more, but it is the most wanted research. And for a long years, he will be appreciated, he will be cited in many places. So, I want you all to do some research on the material side. That is the conclusion. It is one of the beautiful research. When you do work on the materials, the results will be exhilarating. It will be very interesting and very inspiring results will be there. So thank you very much, and I'll be very happy if you have 1 or 2 questions with me.
Session is open for the discussion. Anyone like to ask some questions? Yes.
Sir, good evening, sir. I am a scholar from Anam University, sir.
Very good.
Sir, I want to know about the size and shape of the base material as well as the reinforced material. Have you compared with the size and shape of the material, sir?
Actually, they are solids. They are solid. Both the base materials and the reinforcement material are solids. We purchased all the three materials from Aldrich, I think. The base material they supplied in the form of rods. In the form of rods, you can order any amount. It is only they supply in kilograms, so we can order. And they, based on the packing material, they'll decide the length. Of course, we are not going to use it as such. We are going to melt it. Whatever may be the form, shape, or size doesn't matter. It's going to be melted away. So that is aluminum 6061, and the other materials, they are particles, nanoparticles.
Sir, because the size and shape plays a major role for the hardness and other physicochemical characteristics, so that I have asked you, sir.
Yeah, that is what I told you. The property enhancement will be more for nanomaterials, because the properties are decided by the surface of the particles. Why we got so many peaks in the first case? Because its particle size are less, so they could fix their own boundaries. Some of the boundaries they can break and form a new boundary. Whereas if it is a bulk material, it is not possible.
Okay, sir. Okay, sir.
Thank you. Karthi, we have one person here is known for asking questions.
Good evening, sir. Sir, regarding that corrosion, sir. Actually, aluminum AA6061 is already low corrosion rate.
No, aluminum is corrosive. Basically, aluminum is corrosive.
Low corrosive.
When compared to?
When compared to other materials, that is iron, like that.
Hey.
See then, sir, by adding silicon carbide and boron carbide, you told so many samples is there, sir. One sample corrosion rate is very high. Some samples corrosion rate is less. How this changes happen, sir?
Actually, in material research, only a certain proportion of the constituting material, or we can say the sample prepared only for certain proportion, the properties it shows a tremendous increase. The enhancement of the property will be very high only for a particular combination or a proportion of constitution.
That's why we are going for composites, sir, right, sir? But in this, variation is very high, sir. For a first sample, 120, some samples 270. Corrosion rate is 270. So difference is very high, but base material is same.
Actually, it is determined by the size of the particles that is got into that base material. The size of the particle. It is around now 200 nanometer. If you still crush it and make it 50 nanometer, you will see beautiful enhancement of the property. It is determined by the size, because only that size, only those areas, surface area, interact with the aluminum base material. How much interaction happens, that produces the property, the ultimate property of the material made.
Thank you, sir.
Thank you. Sadish, do you have any question? Please ask. You are from Bangalore. Please ask something. Or give you a comment. You are a scientist. Your profession is doing research. Okay. Any other question from the corner? Mani?
Good evening, sir. We had a very wonderful talk. I have one question. Graphene itself is a very strongest material as on now discovered, and that has been used for various. It has all properties enhanced. It is optical, electrical, thermal, everything. And why you chose that? Because of that. For adding it to a base material, or any reasons for choosing graphene?
Actually, the reinforced materials can be of three types. They can be metal, they can be ceramic, they can be fibrous, they can be a polymer. So,
the known, well-known polymer fiber material for this mechanical properties concerned is graphene one. It has a very good mechanical property. It's very strong material, and that is why we have chosen. But we have chosen it in nanoscale.
We have an animation also in internet. Graphene material is just it's like a honeycomb structure where we have carbon atoms in every vortex, and the thickness of the material is equal to the thickness of one carbon atom. So if you make an elephant stand on a pencil on the graphene, the pencil will break, the graphene will not break. So the animation picture shows that how strong it is.
Okay. Actually here, all the composite materials that we have made, it is the bulk property we are measuring. But graphene, you see, all the properties confined to the nanoscale. So actually, it is the other way we can say. We have tried to bring in the nano property, nano scale material property to the bulk scale. The samples, they are bigger than the laptop. The samples we have made, they are bigger than this laptop. It is a bulk material. Of course, we slice it into small different sizes based on the instrument that we are going to use. We have taken ready.
Thank you.
Thank you, Mani. Thank you very much. Dr. Manikandan was my student 33 years back. My BSc students at Tagore.
Thank you, dear Professor. Dr. S. Periyandi. I hope every presentation in a conference is a work of huge days of someone, a group of work, and presenting within half an hour. 4 years of work, 3 years of work, sometimes 7 years of work is very tedious. And understanding 4 years of work within 45 minutes or 30 minutes is another tedious job. I hope many of you would have, those who are aligned with the research might have understood very well, and those who are not also aligned with the research might have captured some of the concepts. I hope this beautiful lecture was really enriching. I thank Dr. S. Periyandi for presenting this beautiful research. Thank you so much. Thank you for the organizers for the beautiful opportunity. Thank you.
Thank you, guys.
Dear participants, we are waiting for the day to end the session, validatory session. We kindly request your attention to the following instruction to ensure a smooth and dignified conclusion to our event. Please keep your mobile phones on silent to maintain the decorum of the session. Avoid unnecessary movement during speeches and presentation. Participation and appreciation certificate will be distributed at the end of the session. If you are receiving an award or certificate, please come forward promptly when your college name is announced. Official photography and media coverage will take place. Kindly avoid crowding near the stage. Group photographs will be taken at the end of the session. After the formal vote of thanks, we request all the attendees to remain seated for the national anthem. So we are seeking your kind cooperation. Very shortly, the validatory session is going to happen. We are seeking your silence. Thank you. நயனீன்று நன்றி பயக்கும் பயனீன்று பண்பின் தலைப்பிரியா சொல் பிறருக்கு நன்மையை தந்து இனிய பண்பிலிருந்து விலகாத சொல் இம்மைக்கு உலகத்தாரோடு ஒற்றுமையையும் மறுமைக்கு அறத்தையும் கொடுக்கும். Honorable dignitaries, learned delegates, respected professors and students, a delighted afternoon to one and all. It is a time to see the cheerful faces that are ready to decorate our future world to the learnings from this international conference, Nanoscience and Computational Modeling 2025. In these 2 days, we explore the new insights and futuristic advancements. We have witnessed insightful discussions, groundbreaking research and meaningful collaborations in the field of nanoscience and computational modeling 2025. We hope all the excitements and memories that will last a lifetime. So without further ado, let's get started with the audiovisual presentation and make the most of this opportunity, the glimpse of ICNCM 2025.
It is with immense pleasure that I extend a warm welcome to all you to the International Conference on Nanoscience and Computational Modeling ICNCM 2025, organized by the Department of Physics and Chemistry, Sri Manakulavinayagar Engineering College.
Even though there are n number of friendly courses, we all know very well that the basic science is the platform where n number of research amenities come from. So in that case, I would like to say and emphasize here that the Department of Physics and Chemistry have rightly coined the title Nanoscience and Computational Modeling.
So today the SMEC School of Arts and Science is organizing a great event. So any conference nowadays it becomes a knowledge sharing platform. Nanoscience plays a vital role for all aspects.
Use this material a long time ago for various applications.
I personally congratulate for the whole team for having this kind of event in your campus. I'll be delivering something related to the drug discovery. Okay, so I hope you'll enjoy my lecture.
Chemistry department, the physics department, the dean, Dr. Muthulakshmi, have taken an enormous effort to do about it. I wish them all the best. It's a wonderful event to be very successful.
And the conference, it's a great conference. So the title itself, Nanoscience and then Computer Modeling. The great scientist, Sir C.V. Raman, he discovered the Raman effect in 1928. Sir C.V. Raman, he is an Indian. He designed the equipment in India with the cost of less than 500 rupees. Still it is available in ICNCM Kolkata, and he belongs to Tiruchirappalli. So everything is fantastic. One sad information. Now we are purchasing Raman spectrometer from Germany. Now we are purchasing Raman spectrometer from Japan. This scenario we have to change. So that's what Government of India, they have taken mission that Vikshit Bharat. At least from 1947
at least before 100 years, before 2047, can we reach the status of developed nation?
Hello all, myself P. Abhishek David. I am coming from ABM College, Korea. I am a PhD research scholar. This 2 days international conference on nanoscience and computer modeling was very useful to us. I and my research team for this conference. Many topics related to nanoscience, electrochemical related studies like supercapacitors and batteries were very useful. Wishes to this conference organizing committee and team. Thank you.
This is Gandhi Prakash, Assistant Professor in Biotechnology from Indira Gandhi College of Arts and Sciences, Pondicherry. This is my second international conference that I am attending in Sri Manakalona College. I hope this college is entering a new era that every year they are conducting international conference. And that too, it is a wonderful area where they are having a title of nanotechnology and computational modeling, where all the subjects like life science, technology, mathematics, and physics, statistics, almost all the department can accommodate in this conference. This college is entering into a global scenario. Best wishes for the team. Thank you.
என்னோட பேர் வந்து நான் ஆர்ட்ஸ் அண்ட் சயின்ஸ் காலேஜ் படித்தேன். 2 days வந்து இன்டர்நேஷ்னல் கான்ஃபரன்ஸ் அட்டெண்ட் பண்ணியிருக்கோம். ஸோ வந்து நாங்கள் பிஜி பண்ணிட்டு போகிறதுக்கு ஹையர் ஸ்டடீஸ் கொஞ்சம் யூஸ்ஃபுல்லாக இருக்கும்.
I'm Harini from KMC College. நான் 2 days இந்த கான்ஃபரன்ஸ் அட்டெண்ட் பண்ணுறேன். And the topic about nanoscience, which was so helpful. நான் இப்போ பிஜியில் ஃபஸ்ட் இயர் முடிக்க போகிறேன். அண்ட் நானோசைன்ஸை பற்றி கொஞ்சம் வரைக்கும் தெரியாத நிறையா விஷயம் கற்றுக்கிட்டேன். அதுக்கு ஆப்பர்ச்சுனிட்டி கொடுத்து மணக்குள விநாயகர் காலேஜுக்கு தேங்க்யூ.
I am Suresh Kumar. I am from Pondicherry University. Currently, I have participated in the 2 days international conference conducted by Sri Manakulla Vinayakar College School of Arts and Science, and it was very useful. Currently, I am working on the project of synthesis and characterization of nanoparticles, and the topic was nanoscience and computational modeling, and it was very useful. The lectures and the speech was so useful for me, and thanks for the opportunity to Sri Manakulla Vinayakar College. Thank you.
Conferences, definitely everyone should attend, and also we will also conduct this type of more conferences in the future. Thank you for coming to our campus, and thank you once again.
Thank you. To commence this valedictory session, may we request our esteemed dignitaries to grace the stage. May we now request our Honorable Chief Guest, Dean School of Arts and Science, HOD of the Department of Physics and Chemistry, are requested to occupy their dais, the seats on the dais. It is with immense pride and gratitude that we gather here to celebrate the resounding success of this International Conference on Nanoscience and Computational Modeling 2025, a true testament to power of collaboration and shared knowledge. We consider it a great pleasure to invite our endeavor, Dr. S. Muthulakshmi, Dean, School of Arts and Science, to deliver the valedictory note to our gathering.
So very good afternoon. Sathameliye. Good afternoon. So happy everybody? Eppa certificate kudupinga ma'am kelamalam. வெளியூர்லேருந்து வந்தவங்கெல்லாம் கொஞ்சம் பீச் போயிட்டு போகலாம் அப்படிலாம் பிளான் இருக்கா? Okay, anyway, dear students, we have come to the very fine valedictory session of the 2-day International Conference on Nanoscience and Computational Modeling, which is done both in physical and hybrid, online mode. We used to call it as hybrid mode. Yesterday I was here and we were delivering the keynote address. And for those students and our renowned professors who were not there here yesterday, I would like to say that the conference started with the fantastic personalities in the field of physics and chemistry. Yesterday, the professors, the chief guests were Dr. N. Vijayan from CSIR Institute, NPL, New Delhi, Dr. R. Satish Kumar, Principal Research Scientist, IIC, Bangalore, Dr. Catherine from a postdoc researcher from National Sanyat. Today, we have three renowned professors with us. We had, morning I had a meeting with Dr. Ramesh Gardas, professor from IIT Madras. And we had our own supportive professor, Dr. R. Venkatesan, professor of chemistry from Pondicherry University. And then now I'm very happy to invite our Dr. S. Periyandi sir, associate professor, Department of Physics, Kanchima Munivar Center for Postgraduate Studies, Pondicherry. So with this formal invitation, I would like to straight away go to the valedictory address. It's really happy to say that without the support of our management and our beloved director cum principal sir, this international conference would not have come to this much 100% success. The success of a international conference deals with three different factors according to me. Number one, the strength of participants. Yesterday I told it is 450 plus. I think I heard from the organizers that 30 more students have joined today also. So it is near about 480 plus. So the strength of this international conference is really good, and I am congratulating both the departments of physics and chemistry of our college. Reason number two is the strength of an international conference is meant based on the invited speakers. Just now I read 6 different speakers, and apart from those 6 different speakers, many other professors I am meeting yesterday. I'm meeting today, and my own friend Dr. Gandhi Prakash sir is there. Even though he hasn't contacted me, Dr. Satish is here. I am seeing. Yesterday he hasn't. I think I have missed you. With this many happiness we are concentrating in organizing an international conference means a lot. எவ்வளவு ஹார்ட் ஒர்க் அதுக்குள்ள இருக்குன்னு நான் சொன்னேன் ஜெயவர்தன் சார்ட்ட. எனக்கு ஒரு கண்டிப்பாக ஒரு 5லேருந்து ஒரு 10 நிமிஷம் கொடுத்துருங்க சார், மனசில் பட்டதை பேசணும் அப்படின்னு. Yesterday there was no time because we were in hurry. Okay. So second reason is the invited speakers. இன்னமும் ஞாபகம் இருக்கு. Today is March 13th. February 12th or 11th, February 10 and 11 we were in Delhi, and February 11th we invited our Dr. N. Vijayan for this conference as a chief guest. See the effort taken by Manakula Vinayagar in terms of monetary things as well as in terms of the support given to the departments. See, this I think we are privileged in that. So thanking our management for this matter, for this support. Number 3, the last but not least, the strength of a conference depends upon the feedback. So just now I saw the video. It was fantastic. And the content given by each and every feedback, each and every participant is really amazing. இன்னும் நிறைய ஃபீட்பேக்ஸ் நான் எதிர்பார்க்குறேன் இந்த மேடையில். பிகாஸ் இந்த ஃபீட்பேக் கொடுக்கணும்னா இங்கிலீஷில் பேசுகிறவங்க மட்டும்தான் வரணும்னு சொன்னாங்களா என்னன்னு தெரியல. ஒரே இங்கிலீஷாக இருந்தது. அப்படிலாம் ஒன்றுமே கிடையாது. லாங்குவேஜ் இஸ் அ மீடியம் ஆஃப் கம்யூனிகேஷன். அவ்வளோதான். மனசில் பட்டதை எங்கே வேணாலும் திறம்பட சொல்ல தெரிஞ்சா அவங்க தான் ப்ரொஃபஷனல். யூஸ்வலாக எங்கள் டைரக்டர் சார் எங்களை அப்படி தான் சொல்லி வளர்த்துருப்பாங்க. Anyone who is a professional, one who is able to do, able to say, able to communicate effectively what he thinks is a professional. Okay. So now coming to the students. I think ஒரு 450 plus இருக்கீங்கம்மா. யூஜி எத்தனை பேர் இருக்கீங்கன்னு எனக்கு கரெக்டாக ஸ்டாட்டிஸ்டிக்கல் டேட்டா தெரியல. ஐ திங்க் யூஜி நிறைய பேர், பிஜி வந்திருக்கீங்க, எம்ஃபில் அண்ட் பிஹெச்டி ஸ்காலர்ஸ் வந்திருக்கீங்க. ஃபர்ஸ்ட் யூஜி வந்திருக்கவங்க எல்லாமே ஒரு நீங்களே உனக்கு ஒரு கை தட்டிக்கும். ஏன்னா இப்போ ஒரு ஃபீட்பேக்கில் ஒரு ஸ்டூடெண்ட் சொன்னாங்க, she didn't say where from she is coming, but one student was saying I am going to complete my first year UG. ரொம்ப அதிசயம். ஃபர்ஸ்ட் இயர் யூஜியில் ஒரு போஸ்டர் ப்ரெசன்டேஷன் வரணும்னு நினைக்கிறது வந்து எல்லாராலையும் முடியாது. ஸோ அதுக்கு ஒரு மிகப்பெரிய அப்ளாட்ஸ் கொடுக்கலாம். மேபி அவங்களுக்கு யாராவது ஒரு டீச்சரை மோட்டிவேட் பண்ணியிருக்கலாம், ஏன் ஃபோர்ஸ் கூட பண்ணியிருக்கலாம், வா பண்ணு வா பார்த்துக்கலாம் அப்படின்னு சொல்லிட்டு. திஸ் இஸ் வாட் இஸ் த இம்மிடியேட் ரெஸ்பான்ஸ் வி கெட் ஃப்ரம் த இன்டர்நேஷனல் கான்ஃபரன்ஸ். இதை ஏன் நேஷனலாக பண்ணியிருக்க கூடாது, ஏன் இன்டர்நேஷனலாக தான் பண்ணணும் அப்படின்னா, நேற்று ஒரு மேம் வந்தாங்க இல்லையா, பேர் யாருக்கு கரெக்டாக தெரியும் சொல்லி பார்ப்போம். வெரி குட், டாக்டர் கேத்ரின் மேம், வெரி பியூட்டிஃபுல், லவ்லி. இல்லை அவங்க என்ன சொன்னாங்க நேத்திக்கு, பிரேக் யுவர் பவுண்டரிஸ் 7 தடவை சொன்னாங்க அவங்க பேசும்போது. கேர்ள்ஸ்க்கு ஏன் தைவான்லேருந்து கூப்பிடணும், ஏன் மற்ற இடத்துலேருந்து கூப்பிடணும், ஜஸ்ட் டு ஷோ ஆஃப் அப்படின்லாம் இல்லை. இந்த மாதிரி கான்ஃபரன்ஸ் வரும்போது நீ ஒரு நோட் பேட் உனக்கு ஒன்று கொடுத்துருப்பாங்க இல்லையா, அதில் உட்காந்து எழுதுவ சிலது, அப்புறம் அதை தூக்கி போட்டுருவேன். பட் எது உனக்குல நினைவுல இருக்கும்னா, ஆமா இந்த ரெட் கலர் சுடிதார் போட்டு ஒரு மேம் வந்திருந்தாங்க, அவங்க சொன்னாங்க பிரேக் யுவர் பவுண்டரிஸ்னு சொன்னாங்க. நான் ஏன் தைவான் போகக்கூடாது? இப்போ நேத்திக்கு ஒன்று கவனிச்சிங்கன்னா, அவங்க டாக்டர் கேத்ரின் வந்து she has brought her parents yesterday. She is an unmarried lady. பேரண்ட்ஸ் வந்திருந்தாங்க. அந்த பேரண்ட் முகத்துல இருந்த சந்தோஷம் பார்க்கணுமே, அது ஓ பேரண்ட்ஸும் கண்டிப்பா இல்லையா சார்? கண்டிப்பா அந்த அவங்க பேரண்ட்ஸுக்கு இருந்த அவங்க அவ்வளோ படிச்ச மாதிரி தெரியல. ஸோ அவங்க கிட்ட நான் பேசுகிறேன், எப்படி தைரியமாக அனுப்புனீங்க அவ்வளோ தூரம் அப்படின்னு. அவங்க சொல்கிறாங்க, என்ன நம்ம பொண்ணு தானே மேடம், அவங்க கேட்டால் செஞ்சிடணும் இல்லையா, படிக்க தானே கேட்குறாங்க. see how nicely she has been brought up. உங்கள் பேரண்ட்ஸ் கிட்டேயும் இங்கே இருக்கிற எல்லா ஃபர்ஸ்ட் இயர்ஸ்க்கு, செகண்ட் இயர்ஸ், தேர்ட் இயர்ஸ் எல்லா யூஜியுமே போய் சொல்லுங்கள், ஐ வில் டூ மை போஸ்ட் கிராஜுவேஷன் இன் அப்ராட். எங்கள் ஸ்டூடெண்ட்ஸ்க்கு நாங்கள் அதுதான் வந்து சொல்லி வளர்ப்போம். ஐ திங்க் மோஸ்ட் ஆஃப் அவர் ஸ்டூடெண்ட்ஸ் ஆல்ரெடி பிளான்ட். ஒரு 7-8 பேருக்கு ஏற்கனவே பிஜி வந்து கிடைச்சிருக்கு. அதுக்கான ஸ்டடி அப்ராட் ப்ரோக்ராம் எல்லாமே நம்ம கொடுத்துட்ருப்போம் டைம்லி. அது பீரியாடிக்கலாக நடந்துட்டுருக்கோம் பிளேஸ்மெண்ட் டீம்லேருந்து. ஸோ இப்போ நம்ம இன்டர்நேஷ்னல் கான்ஃபரன்ஸ் வரும்போது ஒவ்வொரு ஸ்பீக்கர் கிட்ட இருந்தும் ஒரு பொறி கிடைக்கும். நேற்று டாக்டர் விஜயன் வராங்க, ஒரு தமிழ் ஸ்பீக்கிங் தமிழன், ஒர்க்கிங் ஆஸ் அ பிரின்சிபல் ரிசர்ச் சயின்டிஸ்ட் இன் நியூ டெல்லி. அவர் இவ்வளோ நாள் டெல்லியில் இருந்திருக்காரு, தமிழ் சரியாக வருமா அப்படின்னு யோசித்தேன். பட் எவ்வளோ அழகாக தமிழ் பேசினாலும் நீங்கள் தான் பார்த்தீங்க, நானும் உட்காந்து பார்த்தேன். ஸோ எங்கேயாவது நம்ம மனசில் வந்து ஒரு இக்னிஷன் இருக்கணுமா, எங்கேயாவது ஒரு இக்னிஷன் இருக்கணும். கேர்ள் ஆர் பாய் தடையே கிடையாது, நீ எந்த காலேஜ்லேருந்து வேணாலும் வந்துடு. இப்போ நீங்கள் ஃபீட்பேக்கில் குறை சொன்னாலும் சரி, நிறை சொன்னாலும் சரி, எனக்கு தேவை ஒன்றே ஒன்று தான். உனக்கு எங்கேயாவது ஒரு இடத்துல நேத்திக்கோ இன்னைக்கோ யூ ஷுட் ஹவ் பீன் இன்ஸ்பயர்ட் பை த ஸ்பீக்கர்ஸ். You should have been inspired by either from speaker side or from your own peer group participants. Ma'am கிட்ட கேட்டேன் நான் ஆர்கனைசர்ட்ட, how many posters madam? என்னதான் நம்ம 400 பேர் வந்தாங்கன்னு சொன்னாலும் எவ்வளோ பேர் போஸ்டர்ஸ், எவ்வளோ பேர் வந்து பேப்பர் ப்ரெசென்ட் பண்ணாங்க அப்படின்னும் போது ஆன்லைன் ஆஃப்லைன் ரெண்டுமே சேர்த்து 80+ மேம். நாங்கள் நல்ல விஷயம். ஏன்னா நிறைய பேர் என்ன சொல்லுவாங்க, பயந்துட்டு பேப்பர் ப்ரெசன்டேஷன் வரமாட்டாங்க. ஏன்னா போஸ்டர் ப்ரெசன்டேஷனாவது ஓரளவுக்கு பண்ணிடலாம், பட் பேப்பர் ப்ரெசன்டேஷன் யூ வில் ஹேவ் டு அட்ரஸ் த கொஸ்டின்ஸ் பை த எக்ஸ்பர்ட்ஸ் இன் த ஓப்பன் ஸ்டேஜ். அது கொஞ்சம் பயப்படுவாங்க. அதில் 80+ பிள்ளைங்க வந்திருக்கா அப்படின்றது ரியலி சூப்பர். தென் போஸ்டர்ஸ் வந்து இப்போதைக்கு ஒரு 16 தான், நம்ம ஏற்றி இறக்கெல்லாம் சொல்ல வேணாம், 16 ஸ்டூடெண்ட்ஸ் தான் அப்படின்றது. இதை நாங்கள் வழக்கமாக ஆர்கனைஸ் பண்ணிட்டு இருக்கிறதுனால ஓகே ஒரு 2 days சந்தோஷப்பட்டு விட்டுருவோம். பட் இதோட அவுட்கம் வந்து நீங்கள் தான், உங்களோட பார்ட்டிசிபேஷன் தான். இப்போ நீங்கள் உங்களோட பார்ட்டிசிபேஷனில் நீங்கள் போயிட்டு உங்கள் காலேஜில் சொல்லுங்கள், உங்கள் ஃபேக்கல்ட்டிஸ்ட்டு சொல்லுங்கள், மேம் ஐ வாண்ட் டு மேக் போஸ்டர்ஸ். எனக்கு எப்போ ஆப்பர்ச்சுனிட்டி கிடைச்சோம், இன்னைக்கு மார்னிங் ஒன் ஆஃப் மை ஃப்ரெண்ட் ஹஸ் ஷேர்ட் மீ த போஸ்டர். இதே காலேஜில் 20th அன்னைக்கு there is a பயோகெமிஸ்ட்ரி மீட் அப்படின்னு சொல்லிட்டு வந்திருந்தது எனக்கு. நான் சொல்லிட்டேன் உடனே, யார் விருப்பப்படுறாங்களோ உடனேனா மணக்குள விநாயகர் காலேஜில் ஃபிசிக்ஸ் கெமிஸ்ட்ரி பயோ சயின்ஸ் எந்த காமர்ஸ் எந்த டிபார்ட்மெண்ட்டாக இருந்தாலும் போஸ்டர் பேப்பர்ஸில் வந்து முன்னாடி போய் பார்ட்டிசிபேட் பண்ணுறது நம்மளாக தான் இருப்போம். பை காட்ஸ் கிரேஸ், பை த ட்ரைனிங் ஆஃப் த HOD அண்ட் ஃபேக்கல்ட்டி மெம்பர்ஸ், ஆல்வேஸ் வி அச்சீவ் ப்ரைஸஸ். ஒரு 10 காம்படிஷன் போனாங்கன்னா 8 காம்படிஷனில் ப்ரைஸஸ் வாங்குவாங்க, ஒரு 4-5 காம்படிஷனில் ஓவரால் ட்ராஃபி வாங்கிடுவாங்க. ஸோ இது வந்து எங்களுக்கான மகிழ்ச்சி எப்போவுமே இருக்குது. பட் தென் டு த ஸ்டூடெண்ட் கம்யூனிட்டி ஆஃப் அதர் காலேஜஸ் ஐ ஷுட் சே, நெவர் வேஸ்ட் அன் ஆப்பர்ச்சுனிட்டி. நேற்று கூட நான் சொல்லிட்டு இருந்தேன், பிள்ளைங்க விஜயன் சார் பேசிட்டு இருக்காரு, விளையாடிட்டு இருக்காங்க சார் அப்படின்னு. பட் தென் என்னைக்காவது ஒரு நாள் நீ விளையாடு, நோ இஷ்யூஸ். பட் எங்கே உட்காந்துருக்கோம், எவ்வளோ செலவு பண்ணி வந்திருக்கோம், இதற்கான இந்த கல்லூரி என்ன எஃபர்ட் எடுத்திருக்கு, நம்மளுக்கான டேக் ஹோம் மெசேஜ் என்ன அப்படின்றதெல்லாம் தவற விட்டுறாதீங்க. டு ஆல் த ஸ்டூடெண்ட்ஸ் ஐம் சேயிங், ஈவன் நவ் when I entered inside, all my physics and chemistry students, they are sitting down. அவங்களாம் மேலே கூப்பிட்டு வந்தேன், மேம் இடமே இல்லை, நின்றுட்டு கவனின்னு சொன்னேன். கவனிக்கிறதுல என்ன உட்காந்துட்டு நின்றுட்டு கவனிச்சிட்டா போதும், நம்ம நிற்க முடியாத என்ன. ஒன்லி திங் we have to listen to everything, whoever is speaking. நிறைய பேர் பேசுகிறாங்க, என்னத்தை சொல்லிட்டு போகிறாங்க. See how nicely our treasurer sir was pointing out about 3D folding and all yesterday of proteins. நம்மளுக்கு தெரியும், அவருக்கு being an engineer he is concentrating more on 3D protein folding அப்படின்னா நம்ம அதை பார்க்கணும். So I wish everyone a very grand success in your life. எப்போ என்ன, இப்போ கான்ஃபரன்ஸ் அப்போ மட்டும்தான் இல்லை, எப்போ என்ன ஹெல்ப் பண்ணாலும் எங்களோட HODs கேட்கலாம். உங்களுக்கு என்ன எந்த ஃபேக்கல்ட்டியை தெரியுமோ கேட்கலாம். Everything is open in மணக்குள விநாயகர். So we are all about to serve all the students. And one more last thing what I want to say is, இந்த கான்ஃபரன்ஸை நேத்திலிருந்து ஒத்து பார்க்கும் போதே உங்களுக்கு தெரியும் எவ்வளோ எஃபர்ட்ஸ் எடுத்திருக்காங்க. கண் முன்னாடி இருக்கிற எஃபர்ட் நிறையா, கண்ணுக்கு பின்னாடி நிறையா இருந்தது, அது எனக்கு தெரியும். பட் நேத்திலிருந்து அப்படின்னு பார்த்தீங்கன்னா ஸ்டூடெண்ட்ஸ், ஆக்சுவலி ஃபிசிக்ஸ் கெமிஸ்ட்ரி ஸ்டூடெண்ட்ஸ் எவ்வளோ எஃபர்ட் எடுத்திருக்காங்க. தே ஹவ் கிவன் யூ ஃபுட், தே ஹவ் டேக் கேர் ஆஃப் யூ. அப்புறம் அவங்க போஸ்டர்ஸ் எங்கே ப்ரெசென்ட் பண்ணீங்கன்றது கூட்டிகிட்டு போகிறதுலேருந்து மேபி தவறுதெல்லாம் ஏதாவது தவறு கூட பண்ணியிருக்கலாம், அவங்க கொஞ்சம் தெரியாமல் கூட முழிச்சிருக்கலாம். பட் தென் தே ஆர் கெட்டிங் ட்ரெயின்டு. ஓகே. அண்ட் ஒன் மோர் திங், இப்போ ஒரு வீடியோ பார்த்தீங்க, வீடியோட தரமை என்னன்னு சொல்லலாம். 1 2 3 4 5 பாயிண்ட்ஸ் கொடுத்தா எந்த பாயிண்ட் கொடுப்பேன் இந்த வீடியோக்கு? 0.5 கொடுப்பியா? ஓ 5 பாயிண்ட்ஸ் கொடுத்துருவீங்களா? ஏன் அவ்வளோ பியூட்டிஃபுல்லாக இருந்தது? யார் பண்ணாங்க? We have to congratulate our own Viscom students. Give them a very big hand. ஒரு வீடியோ 2 வீடியோ இல்லை, இதோட அவன் இங்கே சேர்ந்து 3rd year முடிக்கிறதுக்காட்டியும் ஒரு 200 வீடியோஸ் பண்ணியிருப்பான். ஸ்டார்டிங் ஃப்ரம் திஸ் இன்விடேஷன் ப்ரோஷியர் எல்லாத்துலேயுமே அவனோட அந்த ஸ்டூடெண்ட்ஸோட முயற்சி கண்டிப்பாக இருக்கும். ஃபைனலாக ஒரு ஃபினிஷிங்காக நாங்கள் ப்ரொஃபஷனல்ஸ் கிட்ட போவோம், இல்லைன்னு சொல்லலை. பட் மெயினாக ஒவ்வொரு விஷயத்தையும் ப்ரோஷியரில், இன்ஃபர்மேஷன் ப்ரோஷியர்லேருந்து, இன்விடேஷன்லேருந்து, அண்ட் உங்கள் இப்போ நேற்றுக்கு பார்த்த வீடியோ, இன்றைக்கி பார்த்த வீடியோ எல்லாத்தையும் அவன் மேக் பண்ணும்போது ரியலி வி ஆர் ஹாப்பி. பிகாஸ் நாங்கள் ஃபோட்டோ எடிட்டிங் ஃபோட்டோகிராஃபி கற்றுக் கொடுக்குறோம், எடிட்டிங் சாஃப்ட்வேர்ஸ் வச்சுருக்கோம். இது எல்லாத்தையும் யூஸ் பண்ணி இவ்வளோ அழகாக அவனால் பண்ண முடியுதுன்னா, நேற்றுக்கு பண்ணது கூட நான் அவ்வளோ எனக்கு சந்தோஷத்தை கொடுக்கல. ஏன்னா அது ரொம்ப நாள் பிளான் பண்ணி நல்லா செஞ்சது. பட் இன்றைக்கி என்னென்னா, நீங்கள் பார்த்த ஒரு விஷயமும் நேற்று மார்னிங் நடந்து இன்றைக்கி மத்தியானம் நடுவில் எவ்வளோ ஒரு 10 hours 12 hours அவன் அதில் நைட்டெல்லாம் தூங்குனானோ இல்லையோ தெரியாது. எனக்கு நேம் ஆஃப் த ஸ்டூடெண்ட் கூட தெரியாது. ஐ ஷுட் கங்க்ராச்சுலேட் த HOD ஆஃப் விஸ்காம் மேம் ராஜேஸ்வரி மேம், பிகாஸ் யாரை வச்சு பண்ணாங்கன்னே தெரியாது. பட் த டீம் ஹேஸ் டன் அ வண்டர்ஃபுல் இன்சைட். பார்த்தீங்களா எவ்வளோ அழகாக ஃபீட்பேக் வரையும். ஒரு எடிட்டிங் இதில் தான் எடிட்டிங்லாம் நீங்கள் பார்க்கணும். நம்மள்ட்ட இருக்கிற எடிட்டிங் சாஃப்ட்வேர்ஸ் எல்லாம் அவனுக்கு தெரியறதுனால தான் அவன் பண்ணுறான். நாங்கள் எதுவும் வெளியில் கொடுத்தெல்லாம் பண்ணுறதே கிடையாது. இப்போ வெளியில் கொடுத்து பண்ணால் ஒரு ஹாஃப் டேயில் கிடைக்குமான்னு எனக்கு தெரியாது. நேற்று நைட் கொடுத்துருக்காங்க ஃபோட்டோஸ், இன்றைக்கி காலையில் கிடச்சிச்சு, இன்றைக்கி மதியானம் கிடச்சிச்சு. ஸோ திஸ் இஸ் த வே வி டெவலப் அவர் ஸ்டூடெண்ட்ஸ், திஸ் இஸ் த வே வி க்ரோ. And regarding our departments, நான் கண்டிப்பாக சொல்லணும். பட் டாக்டர் ஜெயவர்தன் சார் அண்ட் நேற்று ஈவினிங் எனக்கு கால் பண்ணுறாரு ஒரு 6:45 என்னால் எடுக்க முடியல, நான் இன்னொரு வேலையில் இருந்தனால. திருப்பி நான் கூப்பிட்டு கேட்குறேன், மேம் இல்லை மேம் இன்னைக்கு ஒர்க் முடிஞ்சுது. see the reporting style, see how professional the department is. அதுக்கு முன்னாடி அவரது எடுக்கலையேன்னு சொல்லிட்டு அடுத்தது அவருக்கு பண்ணுறதுக்கு முன்னாடி டாக்டர் சிவரஞ்சனி ஃபோன் பண்ணுறாங்க, மேம் இன்னைக்கெல்லாம் முடிஞ்சது மேம், நாளைக்கு என்னது. they have left the campus by 8 o'clock. எப்போ சாப்பிட்டாங்க, எப்போ இது எதுக்கு சொல்கிறேன் அப்படின்னா, we feel happy in doing something for you. ஸோ இன்னொரு தடவை எந்த ஒரு கான்ஃபரன்ஸ் போனாலுமே, I love you dear students, I request you, I beg you, do not ever never waste your time. ஓகே, இப்போது நம்மளுக்கு ஒரு நல்ல அட்மாஸ்பியர் இருக்குது. பெரியாண்டி சார் சொல்லிட்டு இருந்தாங்க, டாக்டர் பெரியாண்டி சார் இப்போ சொல்லியிருந்தாங்க, மேம் உங்கள் ஆடிட்டோரியம் என்ன இப்படி இருக்குது அப்படின்னு. அஃப்கோர்ஸ் இட்ஸ் அ நைஸ் என்வாயன்மெண்ட், பட் ஹவு குட் யூ ஆர் யூஸிங் இட், ஹவு கம்ஃபர்டபுள் யூ ஆர் அப்படின்றத நீங்கள் பார்த்துக்கோங்க. எத்தனை பேர் ப்ரெசென்ட் பண்ணாங்க, இல்லை நான் ஃபோட்டோவில் பார்க்கும்போது ஒரு சில ஸ்டூடெண்ட் டெபியூ போல் இருக்குது, முதல் முறையாக அறிமுகம். அப்போ அவங்களோட போஸ்டரே அதை காமிக்குது. பட் எவ்வளோ கான்ஃபிடென்ட்டாக அவங்க வராங்க. அந்த பவுண்ட்ரிஸை உடைக்கலை அப்படின்னா எதுவுமே பண்ண முடியாது லைஃப்பில். இன்ஃபேக்ட் நான் இன்னொரு ரகசியம் சொல்லட்டுமா, எங்களோட யூஜியில் எங்களுக்கு இது மாதிரி எதுவுமே தெரியாது. எங்களுக்கு என்ன சொல்லி கொடுக்குறாங்களோ அதை படிப்போம், ஸ்டாஃப் என்ன நோட்ஸ் கொடுக்குறாங்களோ அதை படிப்போம், நல்லா புரிஞ்சிட்டு படிப்போம், வெட்டியெல்லாம் பண்ண மாட்டோம், நல்லா புரிஞ்சிட்டு நல்லா எழுதுவோம், ஹேண்ட் ரைட்டிங் நல்லா இருக்கும். அண்ட் எங்கள் வயசில் எங்கள் எல்லாருக்குமே இருக்கிற ஒரு ப்ளஸ் பாயிண்ட், உனக்கு இனிமேல் இந்த தலைமுறைக்கு இனிமேல் இன்னொரு தடவை கிடைக்காது என்ன தெரியுமா, we all are good in our written and speech communication. நாங்கள் தமிழில் பேசினாலும் பிழை இல்லாமல் இருக்கும், எழுதினாலும் பிழை இல்லாமல் இருக்கும், இங்கிலீஷில் பேசினாலும் பிழை இருக்காது, எழுதினாலும் பிழை இருக்காது. ஆனால் நம்மளோட ஸ்டூடெண்ட்ஸ், உங்கள் யூத் நிறைய தப்பு வரும். நீங்கள் பார்த்தீங்கன்னா தமிழ் இங்கிலீஷெல்லாம் கரெக்டே பண்ண முடியாது, பட் கோர் சப்ஜெக்டில் நல்லா இருப்பான். அது மட்டும் இருக்கக்கூடவே கூடாது. கோரில் நீ இருக்கலாம், நல்லா இருக்கலாம், பட் நீ உன்னோட மொழியில், அது தமிழாக இருந்தாலும் சரி இங்கிலீஷாக இருந்தாலும் சரி, ஏதாவது ஒரு மொழியில் நீ நல்லா பேசவும் எழுதவும் பிழை இல்லாமல் கற்றுக்கிட்டீங்கனாவே யூ வில் பி அட் த ரைட் பாத் அண்ட் ரைட் பொசிஷன். அதுவும் நான் சொல்ல விரும்புகிறேன். பிகாஸ் இந்த யூத்க்கு அதெல்லாம் கொஞ்சம் தெரியல. எனக்கு இல்லை I've got 9 point grade in core அப்படின்னு சொல்லிக்கிட்டு இருக்க முடியாது. We should be very very good in effective communication. Either you speak or write. No, that I have to say. Apart from all these things, I think I have to really congratulate all the winners. இன்னும் எனக்கு சொல்லலை யார் வின்னர்னு, நானும் கேட்கல, அவங்களும் சொல்லலை. ஸோ எனக்குமே அது பெரிய சர்ப்ரைஸ் தான். ஐ வில் பி வெரி வெரி ஹாப்பி இன் டிஸ்ட்ரிபியூட்டிங் ப்ரைஸஸ் டு அவர் பிலவட் ஸ்டூடெண்ட்ஸ் அண்ட் மை ப்ரொனவுன்ஸ் டு ஆல் த ஃபேக்கல்ட்டி மெம்பர்ஸ். இப்போ எல்லாருமே இருக்கீங்க, உங்கள் காலேஜ்லேருந்து கூப்பிட்டு வந்திருக்கீங்க, 2 நாளாக எங்கள் கூட இருக்கீங்க. ஸோ உங்களுக்கு தான் மிகப்பெரிய தேங்க்ஸ் சொல்லணும். ஸோ லெட் அஸ் வைண்ட் அப் திஸ் valediction with very good applause for both physics and chemistry departments. The efforts taken by chemistry பார்த்தீங்கன்னா இப்போ மேகசின் ரிலீஸ் பண்ணாங்க, ஃபிசிக்ஸ் மேகசின் ரிலீஸ் பண்ணாங்க. ஒவ்வொரு விஷயத்துலையும் அவ்வளோ அழகாக இருக்குது. இப்போ மேகசின்னா என்னன்னு அதுக்குள்ளே உட்காந்து ஒர்க் பண்ண பையனுக்கு தெரியும். சப்போர்ட் எஃபர்ட்டு கைடன்ஸ் மட்டும்தான் ஃபேக்கல்ட்டிஸ் கொடுத்துருப்பாங்க, செஞ்சதெல்லாம் ஸ்டூடெண்ட் செஞ்சுருப்பான். அப்புறம் ஒரு ப்ரொஃபஷ்னலாக அதை ஒரு வைண்ட் அப் பண்ணிவிட்டு ஃபினிஷிங் கொடுத்துட்டு நாங்கள் பிரிண்ட் எடுப்போம். ஸோ இதெல்லாம் தான் ட்ரைனிங், இதெல்லாம் தான் வாழ்க்கையில் தேவை. தட் டு தேர்ட் இயர் ஸ்டூடெண்ட்ஸ்க்கு ரொம்ப ரொம்ப தேவை. வித்தவுட் நோயிங் மேகசின், வித்தவுட் நோயிங் வாட் இஸ் நியூஸ் லெட்டர், வித்தவுட் நோயிங் வாட் இஸ் அ கான்ஃபரன்ஸ். ஐ ஹவ் நாட் அட்டெண்டட் எனி த கான்ஃபரன்ஸ்ன்னு நாங்கள் எங்கள் ஜென்ரேஷன் தான் சொல்லியிருக்கோம். ஆனால் எங்களாலேயே இவ்வளோ நல்லா வாழ்க்கையில் வர முடியுதுன்னா, நான் எப்போவும் ஹவ் ஆர் யூ மேம்னா நான் சொல்லுவேன் ஐ ஆம் இன் த டாப் ஆஃப் த வேர்ல்டு அப்படின்னு. தட்ஸ் மை ஆட்டிடியூட். ஓகே, ஸோ அந்த மாதிரி எங்களாலேயே அப்படி வர முடியுதுன்னா யூ பீப்புள் ஆர் ஆல் ரியலி குட் இன் யுவர் ப்ரெசன்டேஷன். இந்த வயசுலேயே ப்ரெசென்ட் பண்ணுறீங்க. ஸோ ஹூ ஸ்டாப்ஸ் யுவர் who limits your growth? So sky is your limit. So dear students, thanks for the opportunity provided. With that I end up with the valediction address. Meeting you soon, expecting you to be in touch with us always. எந்த டிபார்ட்மெண்ட் எது பண்ணாலும் நாங்கள் உங்களுக்கு சொல்கிறோம். பிகாஸ் we have a database. நேற்று நான் படித்தேன் இல்லையா, அதுக்கு தான் ஒரு காலேஜையும் நான் படித்தேன். பிகாஸ் when I spell your college you will be happy. அப்படி எதுவும் விட்டு போயிருந்ததுன்னா மன்னிக்கணும். ஸோ அவ்வளோ காலேஜஸ்க்கும் நாங்கள் will be in touch. Thank you for the opportunity provided.
Thank you, madam, for your inspiring valedictory address. Talent wins games, teamwork and intelligence wins championship. Yes, may we invite M. Aishwarya, research scholar, to announce the details of distribution of prizes and certificates of International Conference Nanoscience and Computational Modeling 2025. A small request, while we are announcing the college name to receive the participant certificates, we humbly request one representative to come forward to receive the certificates. Please cooperate because we have 56 colleges with us to read the names. Thank you.
Under students category, oral presentation, first place goes to Kartika Anand, research scholar from TBML College, Porayar. Second place goes to P. Abhishek David, research scholar from TBML College, Porayar. And the third place goes to RST Bhushan from MSc Biotechnology, Bharat Institute of Higher Education and Research, Chennai. Okay. Under faculty category, oral presentation award, first place goes to R. Jennifer Anjani from SMVC Center of Legal Education. Second place goes to Dr. P. Manimeglai, Sri Manakula Vinayagar Nursing College. Third place goes to Dr. R. Nikita, Jain University of Allied Health Science. Under poster presentation, first place goes to Venkateshwaran from MSc Chemistry, RVS Kumaran Arts and Science College. Second place goes to Ajay Kumar K from Pondicherry University. Third place goes to Gopinath S from Javagar Arts and Science College. Special appreciations to the students of Viscom department, namely S. Gautam, B. Hariharan, Joe Infant Raj, Rohit, Sayan Sudish, Sharan, Akash and Akhilesh for their outstanding contribution in designing our conference brochure and promotional video. While we are announcing the college name to receive the participant certificate, we humbly request one representative to come forward to receive the certificate. Please cooperate as there are 56 colleges. First one, Bharatidasan Government College for Women. Sri Ganesh College for Engineering Technology. First college name, Bharatidasan Government College for Women. Sri Ganesh College for Engineering and Technology. RAC Arts and Science College. Thiru A. Govindasamy Arts College. SMVC School of Arts and Science. Arinyar Anna Government Arts College. Krishnasamy College of Engineering and Technology. Kanchima Munivar Center of PG Studies and Research. St. Joseph College of Arts and Science, Kadalur. Okay. Bharat Arts and Science College. RVS Kumaran Arts and Science College, Dindigul. Indira Gandhi College of Arts and Science. Srinivasa Ramanujam Center, Shastra Deemed University. Srinivasa Ramanujam Center, Shastra Deemed University. Thiruvalluvar Arts and Science College. AVC College, Mayiladurai. IFET College for Engineering and Technology. Periyar Arts College, Kadalur. Dr. Kalainar Karunanidhi Government College, Tagore Government Arts College, Annamalai University, Chidambaram, Pondicherry University Community College. VRS College of Engineering and Technology, Sri Manakula Vinayagar Engineering College, Mailam Engineering College, Manakula Vinayagar Institute of Technology, Pondicherry University, Takshashila University, Christ Arts and Science College, Sarda Gangadharan College, Saint Anne's College of Engineering. Participants maintain silence. I request participants to maintain silence. Participants, please maintain silence. Javagar Science College, Neyveli. SMVC College of Agricultural Studies, Sri Manakula Vinayagar Polytechnic College, Savita School of Engineering, Sri Sevugan Annamalai College, Kaveri College for Women, Davangere University, Manonmaniyam Sundaranar College, Gobi Arts and Science College, Immaculate College for Women. I request the participants to move on to the stage to collect their certificates for the college name which I have read. Bhavendra Bhartidasan Engineering College, Shivaganga College, Sri Meenakshi Government Arts College for Women, Jogamai Deva College, VIT University, Chennai, Srimati Indira Gandhi College, Arifa Institute of Technology, National Engineering College, Srimati Shivanyana Balaya Swamigal College, Nehru Memorial College, Sir Isaac Newton Arts and Science College, Tirukolanchi.
Dear participants, please be seated in your place. I request all of you to be seated, not to go out, because it will disturb the entire event. Please settle down.
Dear participants, we are seeking your kind cooperation. Please not to go out. Remain in your respective seats.
Science college, amma. Okay, இப்போதைக்கு இதை வாங்கிக்கோங்க. Just will
Tirukolonjiappar Government Arts College, Jain University, SMVC Center of Legal Education, University College of Engineering, TBML College of Arts and Science.
அவங்களோட பேர் என்ன?
TBML எங்க? University College of Engineering. TBML இல்ல?
TBML கீழ இருக்க பாருங்க. TBML பண்டார் 7 பேர் 8 பேர் இருப்பாங்க.
முன்னாடியே சொன்னேன். எடுத்துக்கோங்க சார்.
போயிடுச்சு சொல்லுங்க சார்.
I'll give you. வாங்க அப்படி வாங்க.
Thank you, dignitaries. Now, it's time to welcome the participants to share the feedback about our 2 days international conference. Now it's time to welcome the participants to share their feedback about our 2 days international conference. Dear participants, please settle down and maintain silence.
First of all, good afternoon to all. I am Kribavati from Kanjuma Munivar College. I am doing my MSc second year in that college. First of all, thanks for this opportunity. It's very useful to me for this 2 days conference. I learned more, I enjoyed more in this college, in this conference. I learned more from nanoscience topics. And this பெரியண்டி சார் சொன்ன மாதிரி இந்த காலேஜோட அட்மாஸ்பியர் ரொம்பவே சூப்பராக இருக்குது. ஃபுட் இங்கே பார்த்துட்ட ஸ்டாஃப் எல்லாமே நல்லா இருந்துச்சு. ஐ கெட் மோர் ஐடியா அபவுட் இட். நான் என்னோடய ப்ராஜெக்ட் பண்ணுறதுக்கு நானும் நானோ பார்ட்டிகல்ஸில் தான் இப்போ ப்ராஜெக்ட் பண்ண போகிறேன். எனக்கு இந்த நானோ சயின்ஸ் பற்றி இங்கேருந்து இன்ஃபர்மேஷன் வந்து எனக்கு கொஞ்சம் ஹெல்ப்ஃபுல்லாக இருக்கும் என்னோடய ப்ராஜெக்ட்க்குன்னு நினைக்கிறேன், நம்புகிறேன். ஸோ தேங்க்யூ. ஐ எம் ஸோ கிளாட் டு அட்டெண்ட் தி கான்ஃபரன்ஸ் இன் திஸ் காலேஜ். Thank you so much. Thanks to everyone. Thank you staff. Thank you everyone. Thank you.
Thank you, dear.
Good evening to all. The 2-day international conference on nanoscience and computational modeling was a very great experience for the participants. The registration process and time management was well maintained. Thank you for that. All the topic and resource persons were extraordinary, which gave us new and variety of knowledge and valuable insights. Every topic was relevant to the projects which our college make, and it was very helpful to know new things and new tricks. Thank you. The food and hospitality was great. I thank the management on behalf of all the participants for organizing this conference. Thank you.
Thank you, dear. Yeah, thank you for your kind cooperations. And here is one announcement. If any of the college didn't receive your certificates after our national anthem, we are requesting to stand in the first row. To have any issues, to can address with us. Thank you. And achievement is largely the product of steady rise of aspirations and expectation. As a token of appreciation, now we invite Dr. S. Savitri, Professor and Head, Department of Chemistry and convener of this conference, to propose gratitude note for this remarkable event.
Good evening, everyone. Gratitude is not only the greatest of virtues, but the parent of all the others. It is my privilege to deliver the vote of thanks at the conclusion of this successful 2 days international conference on nanoscience and computational modeling, ICNCM 2025, a success. First, I would like to express my deep gratitude to our esteemed chief guests and speakers of today's section. Dr. Ramesh, Professor, Department of Chemistry, IIT Madras. Dr. R. Venkatesan, Professor, Department of Chemistry, Pondicherry University. Dr. S. Periyandi, Associate Professor, Department of Physics, Kanchima Munivar, Government Institute for Postgraduate Studies and Research, Puducherry. Dr. S. Santosh Kumar, Professor, Department of Chemistry, Taiwan. Thank you for your presence, valuable insights and contribution which have greatly enriched today's discussion. We are truly honored to have you here. Thank you, sir, once again. Next, I would like to thank our chief guests and speakers from yesterday's session. Dr. R. Satish Kumar, Principal Research Scientist, Indian Institute of Science, Bangalore. Dr. N. Vijayan, Senior Principal Scientist, CSIR NPL, New Delhi. Dr. Catherine Lim Selvakumar, Postdoctoral Researcher, Department of Physics, National Sun Yat-sen University, Taiwan. Dr. Ramalingam, Department of Physics, AVC College, Mayiladurai. Your expert and knowledge and experience have added immense value to this conference. We are grateful for your time and efforts. Thank you once again. I also extend my special thanks to the International and National Advisory Committee members. Next, I would also extend my sincere appreciation who acted as a jury members for the paper and poster presentation. Thank you. Next, I would like to extend my heartfelt thanks to our management personalities. Their constant support and guidance made this event possible. I am deeply thankful to our Chairman and Managing Director, Mr. M. Dhanasekaran Sir, Secretary, Dr. K. Narayanaswamy Sir, Treasurer, D. Rajarajan Sir, Joint Secretary, Mr. S. Velayudham Sir. Thank you once again. Next, I would like to extend my heartfelt thanks to our beloved Director cum Principal, Dr. V.S.K. Venkatachalamurthy Sir, who constant support and guidance made this event in grand success. Thank you, sir. Next, I would like to welcome our Dean, Dr. S. Muthulakshmi Ma'am, for her consistent encouragement and support. Your involvement have been a key factor in our success, and we are truly grateful to you. Thank you, ma'am. Next, I would like to extend my thanks to Controller of Examination, Dr. Jaikumar Sir, Dean Academics, Anbumalar Ma'am, Arivaligan Sir, Dean R&D, Velmurugan Sir, Dean Placement, Kailasam Sir, Deans of various schools. Thank you all. Next, I would like to express my appreciation to Dr. T. Jayavardhan Sir, Head Department of Physics, for his untiring support and leadership throughout this event. Your dedication has been instrumental in making this conference a reality. Thank you, sir. Next, I would like to thank heads of various departments, staffs who contributed greatly to the success of this conference. Thank you all. A huge thanks to our organizing team, Physics and Chemistry, for their hard work and commitment. You have all gone above and beyond your duties, often stepping outside your comfort zone to make sure everything was perfect. Thank you all. Next, I would like to thank all the participants, staffs of various colleges for joining us in this journey of knowledge sharing and collaboration. Without your active participation, this international conference would not have been the success that it is today. I also wish to thank our faculty members, research scholars, NSS volunteers, technical assistant, and last but not least, students of physics and chemistry for their involvement, whether in organizing, assisting, or participating in the session. Each of you has played a part in making this conference a grand success. Thank you once again, everyone. Have a wonderful evening. Thank you.
Thank you, madam, for your gratitude note. Here is a request. We are requesting Mr. S. Ashokan, research scholar, to come forward to the stage. We are requesting Dr. D. Satish Kumar, Assistant Professor, Indira Gandhi College of Arts and Science, to come into the stage. We are requesting Dr. Gandhi Prakash, Indira Gandhi College of Arts and Science, to come into the stage. Thank you, sirs. Thank you, dignitaries. A small request from us. We are requesting the participants to hand over your feedback form to us while you are relieving the hall. Let us all stand together and be proud to sing National Anthem.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Dear participants, we are requesting to give your feedback form to us and then leave the hall. We arranged